The very concept of a beginning for the universe forces us to confront one of the greatest and most profound mysteries in all of human history. What, if anything, existed before the Big Bang? Understanding the birth of our cosmos is not just an exercise in revealing the deep past. It is a journey that sheds light on our present reality and illuminates the possible futures that lie ahead. This single, profound question has driven scientists for generations to explore the furthest reaches of cosmological mystery, leading to the development of numerous and often competing theories that help us to piece together the grand narrative of the universe's evolution. However, the moment that preceded the beginning, the instant before time and space as we know them came into existence, remains a vast and tantalizing unknown, a frontier of discovery that pushes the very limits of our science and our imagination. The enigmatic presence of dark matter and dark energy, the unseen components that dominate our universe, are further shaping and reshaping our understanding of the fundamental nature of reality. What happened in that unknown period before the Big Bang is not just a question for physicists. It is critical to understanding humanity's true place in the cosmos and the ultimate direction of our collective evolution. Now, we will journey to the very edge of that great question, exploring the theories, the paradoxes, and the profound philosophical implications of the universe's origin. The very concept of time is, for us, the fundamental way in which our consciousness and the physical events of our lives are organized. It is the river on which we float, a constant and seemingly absolute flow from a fixed past to an open future. However, scientifically speaking, time itself may have had a beginning, a moment of birth that coincided with the birth of the universe. According to Albert Einstein's theory of general relativity, time is not a separate, independent entity, but is inextricably intertwined with the three dimensions of space into a single, dynamic fabric known as space-time. The beginning of this intricate and beautiful intertwining is the event we call the Big Bang. This idea, that time and space were born together, could render the very concept of before the Big Bang meaningless, as the word before itself requires the existence of a temporal dimension in which to have meaning. It is like asking what is north of the North Pole. The question itself is built on a framework that ceases to exist at that point. Nevertheless, some compelling and sophisticated theories suggest that time, in some form, may have existed before the birth of our particular universe. For example, cyclical universe models, which have deep roots in both ancient philosophy and modern cosmology, assume that time flows not in a straight line, but in an infinite loop. In these models, the universe undergoes endless cycles of expansion, collapse, and rebirth. In this case, the beginning of our universe would be an illusion, just one turn in an eternal cosmic wheel, and time would continue to exist, in some form, through every cycle. Quantum cosmology theories, on the other hand, offer an even more strange and counterintuitive picture. They argue that time does not have a classical, definitive beginning, but rather that quantum fluctuations transitioned from a timeless, probabilistic state to the familiar, one-dimensional arrow of time that we experience today. This suggests that a kind of proto-time, an immeasurable and non-linear form of existence, may have existed before time as we know it began. Therefore, the profound question, what existed before the beginning of time, is one of the most challenging and mind-bending questions we can ask. A question that straddles the line between science and philosophy. Perhaps the answer lies forever beyond our current understanding of time, in a higher dimensional reality or an entirely different plane of existence that our minds are not equipped to comprehend. Where was the universe before the Big Bang? This question, which seems so simple and so natural, is actually one of the most fundamental and misleading questions we can ask about the nature of space and time. To ask where the Big Bang took place is to assume that there was a pre-existing place, an empty stage on which the cosmic drama unfolded. However, according to our best understanding from modern cosmology. The universe did not happen in a place. The universe created all places. Time and space were born together at the moment of the Big Bang. Therefore, the universe was not in any particular location, because location itself did not yet exist. To think that there was a void, a volume, or an empty space before the universe is a product of our classical, everyday logic, a logic that is built on our experience of a world where things happen within a pre-existing arena. But the origin of the universe challenges the very boundaries of this classical logic. Since space itself was created at that moment, the question of where it was before may not make any logical sense. It is like asking what is outside the surface of a sphere. The surface of a sphere is a finite, two-dimensional space that is complete within itself. There is no outside to it. Alternative theories, however, do offer some intriguing models that give a new context to this question. Theories of a multiverse, or the concept of brain cosmology, suggest that our universe may be just one component, one brain or membrane, existing within a larger, higher dimensional space that contains other universes. In these approaches, our universe may have been born from a collision with another universe, or from a fluctuation within this larger bulk space. In this case, there may indeed have been another plane of existence, another kind of place, before our universe began. Thus, the question, where was it, becomes an investigation into the nature of the cosmic environment in which our universe was born. Ultimately, the question of where the universe was before the Big Bang is not only a physical problem but also a linguistic and philosophical one. It is not the position of the universe that should be questioned, but its very existence. Because before the Big Bang, according to our standard model, there was neither space nor position. What existed before the universe? This question forces us to confront the deeply perplexing concept of nothingness directly. To ask what existed before the universe is to try to understand the absolute boundary between existence and non-existence. Scientists cannot, at present, definitively know whether there was a state of true physical nothingness before our universe came into being. This is because our observational evidence, the light from the most distant galaxies, and the cosmic microwave background, can only take us back to the very first moments of the universe's existence, but not to the moment of creation itself. According to some scientific models, particularly those emerging from quantum cosmology, before our universe existed, there may have been a pure quantum field, a state that is often described as a quantum vacuum. This field may have contained a vast amount of potential energy, which could have then, through a random quantum fluctuation, initiated the birth of the universe. This kind of nothingness is not absolute emptiness. It is a quantum nothingness, a state where the familiar laws of classical physics do not operate, but where the potential for existence is still present. Philosophically, the question what was there before the universe forces us to confront one of the most fundamental questions of all. Why is there something rather than nothing? This is a question that philosophers have been trying to answer for centuries, and it lies at the very heart of metaphysics. The answer may lie in the radical idea that nothingness itself is not a natural or stable state. Perhaps existence is the default, the natural state of being, and the universe is simply the inevitable result of the potential that is inherent in reality. In short, it is still a matter of intense debate whether there was ever a time when the universe did not exist. Perhaps the universe, in some form, has always existed. It has simply changed its form over an infinite amount of time. Or perhaps it really did come into existence from nothing. But this nothing was a state of non-existence that is profoundly different from the simple emptiness that we can imagine. At first glance, the concept of nothingness seems to be a very simple one. It is a state in which nothing exists. It is the void, the abyss, the absolute absence of all things. However, upon closer and more careful examination, This seemingly simple concept is revealed to be deeply and profoundly problematic. In the world of physics, the term nothingness usually refers to a vacuum, which is classically defined as a region of space that contains no energy or matter. However, modern physics, and particularly quantum mechanics, has shown us that even this physical vacuum is not actually empty. Quantum field theory states that the vacuum is a seething, roiling sea of activity, where pairs of virtual particles and antiparticles are constantly and spontaneously forming and then annihilating each other in a fleeting cosmic dance. This means that, at the quantum level, absolute nothingness may never have truly existed. Even the state that we define as nothingness, the vacuum of empty space, may contain a baseline level of energy and constant ephemeral fluctuations. In this context, the term unrealized potential may be a more accurate description of this state than the word nothingness. From a philosophical perspective, the concept of absolute nothingness also creates a deep logical paradox. How can nothingness, a state of complete non-being, give rise to existence? If something can come into being from nothing, then that nothing must have contained the potential for that something to exist. And if it contained potential, then that nothingness was not really nothingness at all. True, absolute nothingness must be a state in which there is nothing, including the very potential for existence. And such a state, by its very definition, should not be able to produce anything that exists. This logical circle suggests that the idea of something arising from absolute nothingness may be a conceptual impossibility. Ultimately, whether we look at it from a scientific or a philosophical perspective, the concept of nothingness is not as simple and as absolute as we might think. The nothingness that may have existed before the Big Bang was perhaps a much more complex, more energetic, and more creative scene than we can currently imagine. A sea of pure potential waiting for the right conditions to blossom into a universe. Although the Big Bang is generally defined in popular culture, and even in many scientific texts, as the absolute beginning of the universe, this definition is actually quite controversial on both scientific and philosophical levels. The word beginning implies a creation ex nihilo, a birth from a state of absolute nothingness. However, according to some of the most advanced and compelling theories in modern cosmology, the Big Bang may have been much more than a simple beginning. It may have been a moment of profound transformation, a transition from a previously existing cosmic order, another form of existence, or even another, older universe. From this perspective, the Big Bang may not have been a birth, but rather a cosmic restructuring, a violent and beautiful metamorphosis. Cyclical universe models, which are gaining increasing attention among theoretical physicists, align perfectly with this idea. According to these models, the universe is a phoenix-like structure that expands, then collapses, and is then reborn in a new fire. This cosmic cycle could last for trillions of years, and each collapse, or big crunch, could trigger the next Big Bang. If this is the case, then the Big Bang that we experienced 13.8 billion years ago was simply a moment of transformation that followed the death of a previous parent universe. This profound idea implies that the past of our universe could be infinite, a concept that fundamentally challenges our ingrained notion of a singular beginning. These ideas also find a deep resonance in the strange and beautiful world of quantum cosmology. In theories of the universe that begin with a quantum fluctuation, there may have been a state of pure quantum potential, something akin to an energy field, that existed before the Big Bang. This potential then, through some as yet unknown mechanism, transformed itself over time to create our universe. This perspective suggests that the universe formed naturally, as an inevitable consequence of the underlying laws of quantum physics, under a certain set of conditions. In this view, the Big Bang becomes a kind of evolutionary leap, not a true beginning from nothing, but an inevitable and natural transition point in the life of the cosmos. Ultimately, the question of whether the Big Bang was a beginning or a transformation is a key that could unlock our deepest understanding of the nature of the universe. If it was a singular beginning, then there is no before to speak of. But if it was a moment of transformation, then there may be a much larger, older, and more complex cosmic structure that lies behind our own universe. A structure whose history may stretch back into an infinite past. As science strives to resolve this profound distinction, we must also seek to make sense of this great unknown by looking at the problem through both the precise lens of physics and the broader, more contemplative lens of philosophy. Modern physics, and particularly Albert Einstein's revolutionary theory of general relativity, states that time is not an independent and absolute entity, but that it exists alongside space, woven together into a single, dynamic fabric. The fabric of space-time, as we now call it, is thought to have emerged and taken shape at the very moment of the Big Bang. Therefore, what we call time may have been born with the universe itself. If this is true, then time was a product of the Big Bang, and there was no dimension of time before it. This leaves us with a rather unusual and mind-bending question: if there is no time, what does the word before even mean? We humans are accustomed to thinking of everything as having a before and an after. But when we reach the very beginning of the universe, this habit of mind may lose its validity. If time itself begins at that point, then there can be no before in any meaningful sense. This is not just a logical dilemma. It is a concept that is deeply and profoundly challenging for our minds to grasp. However, some of the most advanced theories in physics, such as quantum gravity and string theory, suggest that our classical understanding of time as a smooth, continuous, and one-dimensional structure may be an illusion. These theories suggest that time, at the most fundamental, quantum level, may be discrete, made of tiny, indivisible units, or may even be a directionless and emergent property of a deeper reality. In these theories, time is not a universal, fundamental dimension, but a property that emerges from the relationships and interactions between events. In other words, time as we know it may not be what we think it is, but may be a more abstract and complex structure. In this case, there may have been a kind of proto-time, a different kind of temporal order, that existed before the Big Bang. Ultimately, the question of whether time began with the Big Bang remains one of the great unresolved issues in modern science. However, the physical models that we currently have strongly suggest that time, as we experience it, does have a beginning. This beginning represents not only a physical limit of our universe, but also a conceptual limit of our own understanding. Perhaps time is not simply a product of the universe, but is deeply ingrained in its very nature. And to fully understand the nature of time, we will need to understand the universe itself on a much deeper and more profound level. Science, by its very nature, is a discipline that relies on observation, on measurement, and on the empirical testing of our hypotheses. Therefore, it is incredibly difficult, if not impossible, to provide direct observational data about what happened before the Big Bang, a time and a place from which no light or information can ever reach us. However, this does not mean that scientists cannot say anything meaningful about that primordial period. Thanks to the power of our physical theories and the elegance of our mathematical models, a number of different and often competing hypotheses have been developed about what may have existed before the Big Bang. Among these, some of the most well-known and compelling are the models of a cyclic universe, the concept of brain cosmology, the idea of a universe born from a quantum fluctuation, and the theory of an eternally inflating multiverse of cosmic bubbles. For example, according to the cyclic universe model, our universe is not a one-time event, but is part of an endless cycle of expansion and contraction. In this view, the universe expands, then collapses back on itself in a big crunch, which then triggers the next Big Bang, giving birth to a new universe. Each of these cosmic cycles could be seen as the end of a previous universe and the beginning of a new one. In this case, the before of our Big Bang was simply the final, contracting phase of a parent universe. Another, and more exotic, approach is that of brain cosmology, which is inspired by string theory. This theory suggests that our entire three-dimensional universe exists on a giant, multi-dimensional membrane, or brain, and that it was born through the violent collision of our brain with another, parallel brain existing in a higher dimensional space. In this model, the Big Bang is the result of an interaction that occurred in another, higher dimension. Quantum cosmology, on the other hand, offers a more radical and perhaps more fundamental proposal. According to this theory, our universe originated from a vacuum fluctuation at the quantum level. In other words, the entire universe, with all its matter and energy, could have come into existence as a sudden and spontaneous burst of energy in the quantum vacuum, a state of pure potential. In this model, there is no classical before, because time and space themselves would have emerged at the moment of this quantum event. Thus, science is now seriously considering the idea of a timeless and spaceless origin for our universe. While science does not yet have a definitive and proven answer on this profound matter, every new theory that it presents shows us that the beginning of the Big Bang is far more complex, more strange, and more beautiful than we had previously imagined. It may be a mystery that we can never fully and completely understand. However, science does not, and will not, cease to ask these fundamental questions, and with each new question it asks, and each new theory it proposes, it expands the boundaries of our knowledge a little further into the great unknown. Could our universe have been born from another, older universe? This remarkable and mind-bending idea is one of the hypotheses that is gaining increasing attention and credibility in the world of modern cosmology. The theory of the multiverse, in its various forms, argues that our universe is not all that exists, but that it is only one of many, and that other parallel universes may exist alongside our own. If this is true, then it is entirely possible that our universe could have been born from another universe, perhaps from its collapse, or from a quantum fluctuation within its fabric. In this view, our universe would become just one small part of a much larger and more ancient cosmic web. Some theories, particularly those related to the concept of brain cosmology, suggest that our universe was formed by the violent collision of our own brain universe with another parallel brain universe. This cataclysmic collision could have caused a massive and instantaneous release of energy, which would have then led to the hot, dense state of the Big Bang. If this model is correct, then the birth of our universe is actually the result of an interaction that occurred on a much broader, higher dimensional plane. In other words, our universe could be seen as a kind of cosmic child, born from the meeting of two parent universes. Another, and perhaps even more popular, model is the bubble universe theory, which arises from the theory of eternal inflation. According to this theory, new universes are continuously forming, like bubbles in a pot of boiling water, in a background of eternally expanding quantum space. In this scenario, some of these bubbles expand and cool on their own to become full-fledged universes. Like our own, our universe would be just one of these many bubbles. If this is the case, then the birth of our universe could be seen as an entirely random, but physically possible, event. However, there are likely to be fundamental physical laws that govern this process of cosmic randomness, and these laws may operate differently in other different universes. Ultimately, the possibility that our universe was born from another universe offers us a new and radical perspective on the question of our cosmic origins. This idea allows us to see our universe not as a singular, isolated creation, but as a small and perhaps insignificant part of a much larger, and possibly infinite, whole. In this vast and complex cosmic system, universes are born, they expand, they collapse, and they may be replaced by new ones in an endless cycle of creation and destruction. Perhaps our universe is just one single, fleeting link in this endless and beautiful chain of cosmic creation. One of the most intriguing and mind-bending hypotheses about the origin of our universe is the idea that it may have originated from within or under the direct influence of another pre-existing universe. This idea is explored in a number of different theoretical frameworks, particularly those of the multiverse and brain cosmology. If our universe was indeed born from within another, or from a collision with another, this would require us to completely reconsider our understanding of the nature of universes, seeing them not as isolated and independent entities, but as interactive and continuous processes. The other universe that is mentioned in these theories is not merely a place that is physically different from our own. It could be a reality that is entirely and fundamentally distinct in terms of its natural laws, its flow of time, and even its fundamental dimensional structures. In other words, our universe could have emerged as the result of a system that is vastly and perhaps incomprehensibly different from our own. The theories that are known as brain cosmology, or membrane cosmology, have proposed that our entire universe exists on a giant three-dimensional membrane, or brain, that is floating within a much larger, higher dimensional space, often called the bulk. In this picture, the event that we call the Big Bang could have occurred as a result of the violent collision of our brain with another parallel brain. Here, the other universe refers to another brain structure that exists in another dimensional plane, but is capable of interacting with our own. The collision of these two immense membranes could have released a tremendous amount of energy into our universe, much like the friction that is generated between two rocks when they are struck together can produce sparks. This released energy would have then given rise to the matter, the time, and the space of our own universe. This radical idea suggests that the Big Bang was not a singular beginning, but was merely a local event that occurred within a much larger and more ancient system. However, some cosmic clues may bear the faint and subtle traces of such a dramatic scenario. For example, certain large-scale anomalies that have been observed in the cosmic microwave background radiation, such as the so-called cold spot, have led some scientists to consider the possibility that this event may not have been a universal birth, but rather the byproduct of a larger, external event, such as a collision with another bubble universe. Although such observational findings have not yet been clarified and are still highly debated. If we did indeed originate from another universe, this would indicate that our existence is just one small part of a much larger and more complex system. This also implies that our universe came into existence not only through its own internal dynamics, but also through an external interaction. This idea is philosophically striking because it approaches the concept of creation not through a single, absolute first cause, but through a process of continuity and interconnectedness. If every universe is born from another universe, where does this cosmic chain end? Is there an infinite and eternal loop of creation? Or is there a first, triggering universe that started it all? These are the kinds of questions that require us to think deeply, not only about the nature of physics, but also about the most profound philosophical dimensions of our own existence. Perhaps universes, like living organisms, are born, they develop, and they eventually give way to new and different formations in an endless cosmic cycle. When considered within the framework of the strange and probabilistic world of quantum mechanics, the very emergence of our universe could be seen as the product of a single, random event. This idea may seem frightening or even absurd at first glance, as we typically assume that a system as orderly, as vast, and as complex as the universe must have emerged through some conscious, or at least some guiding and deterministic mechanisms. However, in the quantum world, reality operates in ways that do not easily align with our classical, everyday logic. It has been proposed that the universe could have emerged from a state of nothingness known as the quantum vacuum. a state where there is no matter, no time, and no space. Yet it still contains a vast reservoir of potential energy, as a result of a single, random quantum fluctuation. This potential could have been realized. This accidental creation hypothesis was first proposed by the renowned physicist Edward Tryon in the 1970s. Tryon famously asked, "Why shouldn't the universe be a quantum fluctuation?" This perspective views the origin of the universe as an unexpected, yet physically possible, outcome of the inherent energy fluctuations that exist in a quantum vacuum. In other words, the universe could have accidentally come into existence as a system with a net energy of zero, provided that its positive and negative energy components remain in perfect balance. In such a model, no external cause is required for the universe's emergence. Probability alone is sufficient. However, the emergence of a highly ordered and structured universe from this initial, accidental formation remains an unresolved and deeply perplexing question. The fact that our universe not only exists, but is also exquisitely and finely tuned to allow for the existence of life, raises the profound question of whether this initial randomness was somehow limited or directed. For this reason, the idea of an accidental formation is often considered alongside other concepts, such as the anthropic principle, perhaps among billions of other failed universes that may have also fluctuated into existence. The only one that has the right order and the right laws to allow for the emergence of life is our own. In this view, we are here simply because we can be here. If the universe were any different, there would be no one to observe it. Therefore, the idea that the universe arose by chance becomes not only a physical question, but also a deeply existential one. If everything is the result of a cosmic roll of the dice, how does this affect our place in the universe and our search for meaning? Is the emergence of conscious beings in a universe that came into being by chance a true miracle? Or is it simply a part of the universe's grand and impersonal game of probabilities? Such questions demonstrate that our scientific models of the nature of the universe must go hand in hand with deep and careful philosophical thought. Time is one of the most fundamental and essential building blocks of our perception of reality. Everything we experience, everything we remember, everything we plan for, flows and is organized based on the relentless and seemingly one-way arrow of time. Our memories remain in the fixed and unchangeable past, and our plans are directed toward an open and uncertain future. However, the question of whether time is an objective and fundamental feature of the physical realm, or is merely a product of our perception, a kind of grand illusion, is still a matter of intense and ongoing debate. In some of the most advanced and speculative theories in physics, time is considered not to be a fundamental property of the universe itself, but rather a context that is defined by the observer in relation to the events they witness. In this case, time may not actually exist as a fundamental entity, and our experience of its passage may be merely a result of our own consciousness and our interaction with the universe. In particular, studies in the field of quantum gravity have suggested that time is not a universal, absolute dimension, but is a process that can vary and even break down depending on the events and the scales at which they are observed. Some models, such as string theory, argue that time is not something fundamental, but is merely a derivative property that emerges from deeper and more complex physical processes. If this is true, then a reality that exists outside of time is not just possible, but may be the fundamental state of the cosmos, and the origin of our universe may have occurred from this non-temporal plane. This perspective suggests that the very concepts of before and after, which we use to describe the origin of the universe, may be deeply and fundamentally misleading. Additionally, some cosmological scenarios have been proposed that assume the universe had a timeless beginning. For example, the famous no-boundary proposal, developed by Stephen Hawking and James Hartle, suggests a quantum mechanical model in which the universe has no definitive starting point, and in which time is curved and finite, much like the surface of a sphere. According to this model, the past of the universe is not a singular point, but a smooth, rounded surface. In this case, time as we know it may not have existed in the classical sense at the very beginning of the universe, and it may have only emerged as a distinct and linear dimension as the universe began to expand and cool. The possibility of a reality that exists outside of time is a concept that is quite difficult for the human mind to comprehend, as we are hardwired to conceptualize everything in terms of a linear and forward-moving timeline. However, the laws of physics themselves suggest that the universe does not have to operate in this familiar way. If there is indeed a reality outside of time, then perhaps the true origin of the universe lies in this timeless plane. This could completely and fundamentally redefine our concept of a beginning. Perhaps, to truly understand the birth of our universe, we need to start thinking beyond the confines of time itself. If time did indeed begin with the universe, then there must have been some element or some event that triggered its beginning. However, this very idea contains its own deep and perplexing paradoxes. How can a thing exist before time begins? For that thing to exist and to have an effect, it would seem to require a temporal framework in which to act. For this reason, many scientists do not rely on the classical linear relationship of cause and effect to explain the beginning of time, but rather on a more fundamental physical or quantum transitional process. Perhaps what initiated time was not a cause in the sense that we normally understand it, but was rather the spontaneous realization of a natural, inherent potential. Quantum cosmology models provide a strong and compelling foundation for this very idea. For example, the concept of the universal wave function, a central idea in quantum cosmology, argues that the entire universe transitioned from a timeless, probabilistic quantum state to a classical, deterministic universe. This transition can be thought of as a kind of cosmic scale wave function collapse. In this view, time may have emerged as a direct result of this collapse. In this case, the ultimate initiator of time could have been a purely quantum event, one that occurred spontaneously and without a prior cause when a certain energy level was reached. It does not require any conscious or external cause, but is based solely on the principles of physical necessity and quantum probability. According to another, related hypothesis, time may have emerged as a direct consequence of the expansion of the universe. In other words, as space began to expand, time began to flow. This model suggests that time is not a fundamental driver of cosmic events, but is a byproduct of the dynamic and evolving behavior of the universe. In this sense, time is not the motor of the universe, but is an emergent property of its motion. Without the expansion of the universe, time itself would not exist. This leads us to view the beginning of time not as a singular cause, but as a fundamental condition of our universe's existence. While all of these theories are attempting to explain the beginning of time from different perspectives, they all share a common and profound thread: time may have emerged suddenly. But this emergence is not a process that can be easily explained by our familiar, classical cause and effect relationships. To truly understand the origin of time, we may need to approach its very nature in a completely different and more fundamental way. Perhaps time is as fundamental to our very understanding of the universe as it is to the universe's own emergence. We usually think of time as an abstract and unchanging framework, a kind of invisible grid on which the events of the universe play out. But modern physics, and in particular Albert Einstein's theory of general relativity, has deeply and profoundly questioned this classical concept. General relativity has shown us that time is not absolute, but is a dynamic and malleable quantity that can be bent and warped by the presence of mass and energy. This demonstrates that time is not merely a passive flow, but is an active and interactive dimension of the material universe. Even if time itself is not a form of energy, if it is so directly and intimately related to energy, then it is possible that time emerged, or was produced, alongside the emergence of matter and energy at the beginning of the universe. This idea strongly supports the possibility that time, like everything else, could have had a definitive beginning. When we consider the very origin of the universe, Studies in the field of quantum gravity suggest that time might be a derivative property of the fundamental energy fields that existed at the beginning of the universe. In the very first moments, below the so-called Planck time, which is approximately 10 to the power of minus 43 seconds, time and space could not be defined in the classical sense. At this incredible scale, energy is so dense and so concentrated that the very fabric of space-time is thought to merge with the chaotic and roiling sea of quantum fluctuations. This means that time had not yet emerged in its familiar, classical sense, but may have had a quality that evolved and changed alongside the evolution of energy itself. Perhaps time became organized and gained its familiar, linear flow only as the universe began to expand and cool, and as the primordial energy began to distribute itself into more stable and structured forms. If time is indeed a phenomenon that is deeply and fundamentally connected to energy, this holds significant and profound clues not only about the beginning of our universe, but also about its ultimate future. It is possible that time itself may change as the energy structure of the universe dissolves, as entropy increases and the universe approaches its final state of heat death. The very flow of time may slow down, or even stop, or perhaps change its direction. In this context, it can be thought that the direction of the arrow of time is determined not only by the sequence of physical events, but also by the general course of the distribution of energy in the entire universe. Such an approach suggests that time is not merely the passive sequencing of events that occur within the universe, but is also a direct and active result of the universe's own energetic structure. Philosophically, this view makes the question of what existed before time much more meaningful. If time is also a phenomenon that emerged later, just like matter and energy, then the question, what was there before time began, can be transformed into a more physical and perhaps more answerable question: what was the nature of energy before it gave rise to time? This subtle but important shift in perspective moves us away from purely metaphysical and abstract thinking and brings the question of the beginning of the universe into a more measurable and experimentally investigable realm. When we consider that the universe is not merely a collection of matter, energy, and space-time, but that it also contains a vast and ever-increasing amount of information, we arrive at a more complex and multi-layered reality. Information, in this context, is the sum of all the order, the structures, the physical laws, and the possibilities that exist in the universe. From the perspective of quantum physics, every single particle in the universe carries information through its wave function, which describes its state and its probabilities. Therefore, the moment of the universe's birth may not have been only a physical beginning, but also the birth of information itself. In a very real sense, the entire universe can be perceived as a vast and complex data set. The positions, the speeds, the interactions, and the probabilities of all the particles that make up the cosmos, all of these elements, may have been encoded in the very first moment of the universe's existence. This profound idea is particularly explored within the framework of the holographic principle. According to this speculative but powerful principle, all of the information that is contained within a volume of the universe may be completely encoded on the boundaries of that volume, on a more fundamental two-dimensional plane. If this information did indeed emerge at the very beginning of the universe, then the Big Bang could have been not just a release of immense energy, but also a kind of cosmic decoding process. It is analogous to a computer loading its operating system after its basic input-output system, or BIOS, has been initiated. In this view, the universe might have started with a fundamental matrix of information, a kind of cosmic code that contained all the necessary laws, constants, and probabilities that would determine how the universe would operate and evolve over time. We can also reach some interesting conclusions about the role of information through the concept of entropy. As entropy increases, the overall order of a system decreases, but the information it contains is not lost. It simply becomes more disordered and harder to access. Therefore, the existence of a very low entropy, highly ordered state at the beginning of the universe indicates that it must have contained a very high level of structured information. With the expansion and evolution of the universe, it is thought that this initial information has been dispersed and transformed into the vast and complex structures that we see today: the galaxies, the stars, the planets, the DNA of living organisms, and even consciousness itself. All of these are the complex and beautiful evolutionary results of that initial, compact core of cosmic information. From a philosophical perspective, this view forces us to re-examine the very meaning of the universe and its relationship with consciousness. If information is an inherent and fundamental property of the universe, this could indicate that the universe is not a random or chaotic system, but has a deeply information-oriented structure. Perhaps the universe is evolving in a way that is designed to produce and process information, and to eventually observe itself through the emergence of consciousness. This idea opens the door to the concept of a cosmic purpose. Information could be the universe's way of communicating with itself, of becoming aware of its own existence. In this grand and beautiful picture, the Big Bang was not just a beginning, but also a kind of end. The Big Bang is traditionally and widely accepted as the moment of the universe's birth, the beginning of all things. However, some of the most advanced and compelling theories in modern physics suggest that this cataclysmic event may not have been just a beginning, but may also have been the end of a previous, older universe. This profound view is particularly common in the cyclical universe models that we have explored. In this picture, universes are born, they expand, they collapse, and then they are reborn in an endless cycle. The Big Bang may have been the first brilliant spark of a new cosmic cycle that followed the Great Collapse, or the Big Crunch, of a previous parent universe. This suggests that the universe is not a one-time, singular formation, but is a constantly renewing and evolving system. One specific type of these cyclical models is the Big Bounce model. According to this model, at the point where a previous universe collapsed due to its own immense density, time and space were, in a sense, reset, and then a new expansion began through the powerful effects of quantum gravity. Our universe, in this case, would be the result of this cosmic bounce. The Big Bang is therefore both a moment of birth and a moment of death. It is thought that some of the information, the energy, or even the fundamental structures from the previous universe could have been transferred to our own universe through this bounce. In this view, our universe is not entirely new. It may be the heir to a previous, long-lost existence. If the Big Bang is indeed the beginning of an end, this idea also fundamentally redefines our understanding of the nature of time. Time may not be a linear and one-way street, but may be cyclical, like a great cosmic wheel. Each universe begins and ends its own particular chapter of time, but the overall process of time itself may be eternal. In this case, the very concept of an absolute beginning and an absolute end becomes meaningless. Everything in the cosmos exhibits a profound continuity through a constant process of change and transformation. This also provides us with a deeper and perhaps more comforting insight into the meaning of existence itself. In this picture, death is not an absolute annihilation. It is merely the gateway to a new and different birth. This view is a powerful one, both scientifically and philosophically. The profound symmetries that are observed in our universe, the conservation of its physical constants, and the relentless and mysterious arrow of time may all bear the faint and subtle traces of a cyclical and eternal system. In such a system, the future of our universe may be to inevitably return to its own beginning. Perhaps the universe that we are currently experiencing is just the last, fading cry of the past, and at the same time, the very first, brilliant breath of the future. Whether time has a definitive beginning is one of the most fundamental and deeply debated questions in all of modern science. If time did indeed begin suddenly, at an absolute and singular 0 point, then everything that existed before that point would be undefined, or perhaps non-existent. However, is this 0 point truly absolute? Or is it merely a relative reference point in a much larger and more complex cosmic story? The event that we call the Big Bang, which is widely accepted as the beginning of our universe, was not actually an explosion in the classical sense. It was the moment when space-time itself began to expand. Therefore, when we speak of the beginning of time, we may actually be referring to a moment of transition rather than a singular physical event. In modern cosmology, the Planck time is generally accepted as the effective 0 point of time, as far as our current physics can describe. This is an incredibly and almost unimaginably short duration. Approximately 10 to the minus 43 seconds after the Big Bang, we have no definitive information about what may have come before this point. This is because the current laws of physics, including Einstein's general theory of relativity, lose their validity at this extreme scale. However, at this point, the very term beginning may be more of a reflection of the boundary of our current knowledge than a statement about the true nature of reality. Perhaps time gained its familiar, continuous flow by crossing this quantum threshold. In other words, time did not suddenly emerge from nothing. It may have gradually taken shape from a more fundamental, timeless state. This suggests that the emergence of time was not a birth, but a formation. Some of the most advanced theories in physics propose that time may have already existed in a different and unfamiliar form at this so-called 0 point. According to these theories, time may have existed in a different dimension or as a different kind of structure before the birth of our universe. With the expansion of the universe, it began to flow in the linear way that we are familiar with, and we are now witnessing it in this particular form. In this case, the 0 point is merely a moment of rupture in our own perception of time. In reality, time itself may have been a much more complex and multifaceted entity. This debate is not only a scientific one, but also a deeply metaphysical one. The idea of an absolute 0 point for time implies that the universe was created, and that this creation was a singular event that was limited to a single moment. However, the idea that time is a process suggests that the universe came into existence through a more natural and gradual development. This, in turn, leads us to rethink our most fundamental concepts, such as creation, cause, and purpose. The fundamental question of whether time is an absolute and fundamental feature of the universe, or an emergent and relative one, continues to drive the frontiers of both physics and philosophy. Symmetry breaking is a critical and profound concept in modern physics, and it is especially important in the field of cosmology. It is thought that in the very first, incredibly hot and dense moments of the universe, all of the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces may have behaved as a single, unified superforce. This primordial period was characterized by extremely high temperatures and energy levels, a state of perfect and beautiful symmetry. However, as the universe began to expand and cool, these unified forces began to separate and to differentiate from one another. This process is what physicists call symmetry breaking. In other words, while the universe initially possessed a state of perfect and profound symmetry, this symmetry gradually and inevitably broke down, giving rise to the rich and complex diversity of forces and particles that we observe in the universe today. The process of symmetry breaking does not merely signify the separation of the fundamental physical forces, it also led to the crucial imbalance between matter and antimatter, the emergence of mass itself, and the formation of the fundamental structural foundation of the entire universe. For example, it is thought that particles gain their mass through their interaction with the Higgs field, a process that is itself a result of a specific kind of symmetry breaking. If this symmetry had not been broken, then all particles would be massless, and neither atoms, nor galaxies, nor stars, nor life itself could have ever formed in the universe. Therefore, All of the incredible diversity and complexity that we observe in the structure of the universe today is the direct result of a series of microscopic imbalances and symmetry-breaking events that occurred in those first, fleeting moments of cosmic time. How these breaks in symmetry occurred at the quantum level is still not fully understood. However, our mathematical models suggest that these breaks were not chaotic or random, but that they occurred within a specific and well-defined set of rules, and were governed by a highly delicate distribution of energy. In other words, the asymmetrical and complex structure of our universe is actually a broken form of a much deeper and more delicate underlying symmetry. What is so intriguing is that this process of breaking was not random, but was the product of a specific and inherent physical logic. This shows us that the universe has a fundamental structure that simultaneously contains both a deep and profound order and an incredible potential for diversity. The concept of symmetry breaking also has deep and resonant philosophical implications. The universe that emerges from the breaking of a perfect and pristine symmetry is similar to a work of art that gains its unique beauty through a deliberate and well-placed flaw. According to this idea, it was the universe's very deviation from a state of sterile perfection that brought with it the fundamental characteristics that make our cosmos a habitable and life-bearing place. Perhaps existence itself, in all its messy and beautiful complexity, is only possible through the conscious or unconscious breaking of a perfect and underlying symmetry. The laws of physics, as we understand them, determine the fundamental rules of all the events that we observe in the universe. However, the question of when and how these elegant and powerful laws came into existence remains one of the great and enduring mysteries of science. Many scientists believe that the laws of physics were established at the very moment of the Big Bang, or in the first few fractions of a second that followed. In other words, it was not only matter and energy that came into existence with the birth of the universe, but also the fundamental and immutable laws that would govern the behavior of these materials for all of time. This suggests that physical reality consists not only of content, but also of a set of inviolable rules. The Big Bang may have created not only the matter of the universe, but also the very rules of the cosmic game. However, this idea raises some very deep and difficult questions. Are the laws of physics independent of the universe, or did they emerge with the universe itself? In other words, do these laws exist in some abstract, timeless, Platonic realm, above and beyond the universe, or are they an integral and emergent part of it? If they are independent of the universe, this seems to place them in a metaphysical realm that is beyond the reach of science. If they are an integral part of the universe, then this opens up the possibility that they are not fixed and immutable, but are dynamic and could even be evolutionary. Some physicists have therefore suggested that the laws of physics themselves may have evolved over time. Perhaps these laws were different in the very early and extreme stages of the universe, and the rules that we observe today are the ones that stabilized over the course of cosmic time. Another intriguing and related question is why the laws of our universe seem to be so exquisitely and finely tuned to allow for the existence of life. Even a very small and seemingly insignificant change in the value of the fundamental physical constants could have made the formation of complex structures impossible. This delicate and seemingly improbable balance has led some scientists and philosophers to believe that the laws of physics did not arise randomly, but through some specific and underlying logic or necessity. Perhaps, as the multiverse theory suggests, there are many other universes where different physical laws apply, and the laws in our particular universe are observable by us only because they are the ones that allow for life to exist in the first place. This also implies that the Big Bang could have been a moment of cosmic selection, a process that determined which of the many possible sets of universal laws would allow for a stable and continuing reality. The relationship between the laws of physics and the beginning of the universe is a profound debate that brings science and philosophy into close and intimate contact. If these laws were indeed written at the very beginning of the universe, then we are talking about a kind of cosmic software. But who, or what, wrote this software? Or did the universe, in some strange and beautiful way, code itself. These are the kinds of questions that have both deep physical and profound ontological dimensions, and they continue to guide us in our quest to understand the fundamental nature of our universe. The Big Bang Theory is often associated with the concept of a singularity. A singularity in this context is a point where time and space are thought to have been compressed into a zero volume, and where the density of matter and energy was infinite. However, this very concept represents a point where the current and well-tested laws of physics, including Einstein's general theory of relativity, no longer apply and cease to make sense. In other words, a singularity is actually an unknowable limit of our theories, a mathematical artifact that signals the breakdown of our physics, rather than a true description of physical reality. For this reason, some of the most prominent physicists in the world have begun to question whether a singularity actually existed at the beginning of the universe. Perhaps the beginning of the cosmos was not a point of infinite density, but rather a different and more complex structure, with distinct physical properties that may be defined by the laws of quantum gravity, a theory that we have yet to fully understand. According to some of these theories, the singularity is a consequence of our classical, and therefore incomplete, understanding of physics. However, in the framework of quantum gravity models, this problematic infinity may be replaced by a more stable and definable transition region. For example, the concept of a Planck foam or a quantum spacetime structure argues that spacetime itself is not a smooth and continuous fabric, but is discontinuous and foamy at the smallest possible scales. In this picture, these fundamental quantum structures would replace the classical singularity. In this case, before the Big Bang, there was not a void or a nothingness in the classical sense, but rather a realm of highly dense and energetic quantum fields. Alternatively, some theories have proposed that our universe sprang back into existence after the collapse of a previous parent universe. In this model, the singularity is not an end or a beginning, but a transition point, like a spring that compresses to a maximum and then expands again. In this view, the universe moves in an infinite number of cycles. This approach proposes a cosmology in which the singularity is negated, and the universe exists as a continuous and eternal entity. In such cyclical models, time is also continuous, which means that the concept of before the Big Bang once again gains a real and meaningful sense. Philosophically speaking, the very concept of a singularity takes us both to the absolute limits of our current scientific knowledge and beyond the very bounds of our human imagination. If the singularity is merely a hypothesis, a placeholder for our ignorance, then perhaps we need a very different, more intuitive, and more conceptual understanding of the true origin of our universe. The idea that something other than a singularity could have existed before the Big Bang is a profound challenge that is pushing the boundaries of modern science and is requiring us to develop larger, more comprehensive, and more beautiful models to understand the deep and mysterious nature of our universe. The idea that the entire universe works like a vast and complex information processing system is a concept that has been intensely and increasingly debated in both scientific and philosophical circles, especially in recent years. According to this radical and compelling approach, the universe does not merely contain energy and matter, it also produces, processes, and stores information, much like a giant cosmic computer. In this framework, the universe can be seen as having all the components of a computational system. It has input data, which are the initial conditions of the universe. It has processors, which are the fundamental laws of physics, and it has outputs, which are the complex structures that we see today, including consciousness and life itself. This idea is gaining increasing acceptance and support, particularly within the framework of quantum information theory and the holographic principle. In this view, information lies at the very core of the universe. Matter and energy may be just the physical manifestations of this more fundamental, informational reality. According to this approach, every single physical event that occurs in the universe is, At its heart, a process of information processing. For example, the collision of two elementary particles is not merely an exchange of energy and momentum, it is also a transfer and a transformation of information. In this view, information exists not only in the written or digital systems that we create, but is an inherent and fundamental property of nature itself, existing within the hearts of stars, in the elegant spirals of our DNA, and in the strange and beautiful world of the quantum fields. If this is true, then to understand the fundamental workings of our universe, we would require not only the tools of physics, but also the principles of information theory. The processing of information may be a fundamental property of the universe at both the smallest, microscopic scales and the largest, macroscopic levels. The holographic principle, a speculative but powerful idea from string theory, seems to reinforce this concept. According to this principle, all of the physical information that is contained within a three-dimensional region of space can be completely and perfectly stored on its two-dimensional boundary surface. This implies that the universe itself could operate like a giant and complex hologram. Every point in the universe may, in some way, carry information about the whole. In this case, we ourselves would be a form of data processor existing within this vast information system. The human mind, in this picture, may be a highly evolved and specialized information point, a way for the universe to recognize, to process, and to recode itself. This profound idea takes the relationship between consciousness and the universe to a whole new and exciting level. If the universe is indeed an information processing system, then could this system have a purpose or a direction? Perhaps the universe is constantly trying to establish a kind of balance by producing more and more complex information to counteract the relentless increase of entropy. Or perhaps the universe itself is not conscious, but it operates in such a way as to make room for the emergence of structures, like living beings, that can continue the process of information processing. These are the kinds of thoughts that are deepening both our scientific and our metaphysical inquiries. Perhaps the universe exists for the sole purpose of reaching a state where it can produce information processors that are advanced enough to understand it. The concept of nothingness is perhaps one of the most challenging and perplexing ideas for the human mind to grasp. This is because we are so accustomed to thinking about things, to imagining entities, or to contemplating states of being. However, the concept of nothingness represents a state in which there is no time, no space, and no existence of any kind. Can such an absolute nothingness really exist? Or is it merely a mental abstraction, a concept that has no counterpart in reality? The answer to this profound question is of great importance at both the philosophical and the physical levels. Because if a state of absolute nothingness did indeed exist before the Big Bang, then the very emergence of something from this nothingness would shake the very foundations of all the cause and effect relationships that we know and understand. Physically speaking, even an absolute vacuum is not actually a state of true nothingness. According to the principles of quantum field theory, the state that we call the vacuum of empty space is actually filled with a seething sea of energy and is constantly creating pairs of virtual particles and antiparticles. This shows us that a state of true, absolute nothingness, a state with zero energy and zero activity, cannot be observed in nature. There is no region of the universe that is at absolute zero temperature, or is completely and utterly devoid of energy and motion. If a state of absolute nothingness is truly impossible, then there must have been something that existed before the Big Bang. Perhaps this something had a structure that was very different from our classical physical intuition. Philosophically, the concept of nothingness is also deeply controversial and paradoxical. The very question, if there is nothing, who or what is observing it, brings up the deep and intimate relationship that exists between existence and consciousness. Perhaps the very concept of nothingness can only be defined by the existence of something. In this view, nothingness only gains its meaning in contrast to the concept of existence. In this case, The idea that a state of true and absolute nothingness cannot exist becomes even stronger. Perhaps existence is nothingness denying itself. Such thoughts open the door to deep and intuitive questions about the fundamental nature of our universe. Scientists have developed a number of different and often competing theories to try to answer the profound question of how something can come from nothing. According to some of these theories, quantum fluctuations in a primordial vacuum made it possible for our universe to emerge. However, the important and subtle point here is that even this quantum vacuum is not actually a state of true nothingness, because the laws of physics and the quantum fields themselves are still thought to be present in this state. Therefore, even the vacuum state that is often presented as the ultimate starting point of the universe contains a deep and underlying order and a vast potential for existence. This shows us that the concept of absolute nothingness may be nothing more than a useful, but ultimately misleading, concept.
Imagine standing at the edge of an abyss, a place of such profound emptiness that it seems to contain nothing at all. No light, no sound, no matter, not even the familiar framework of space and time. This is the conceptual void from which our entire universe, in all its vastness and complexity, is thought to have been born. It is the ultimate mystery, the question that has haunted philosophers, poets, and scientists for millennia. Why is there something when there could have been nothing? As you gaze up at the star-dusted canvas of the night sky, you are not just looking at distant points of light, you are looking back in time, at the echoes of a cosmic story that began with a mystery so deep it challenges the very limits of human understanding. And yet, modern physics has begun to peel back the veil of this nothingness, and what it has found is not an empty, passive stage, but a vibrant, seething, and endlessly creative reality. The void is not a void. It is a quantum sea, a turbulent ocean of energy and potential, a place where the rules of our everyday classical world dissolve, and a stranger, more fundamental logic takes over. This is the realm of the quantum vacuum, a place where particles can be in many places at once, where they can be connected across vast, cosmic distances in an instant, and where the very act of observation seems to shape the nature of reality itself. This strange and beautiful vision of a potent, creative emptiness is not a new idea. It is a concept that has resonated through human history, an intuition that has found expression in some of our most ancient philosophical and spiritual traditions. The ancient Greeks spoke of chaos, the formless, primordial abyss that existed before the ordered cosmos. In the rich contemplative traditions of the East, we find even more striking parallels. The Hindu concept of shunyata, often translated as emptiness or voidness, is not a nihilistic concept of non-existence. It is the understanding that all phenomena are devoid of any fixed, independent self-nature, and that they arise from a common, underlying ground of being that is itself empty of any inherent characteristics, yet full of infinite potential. The Tao Te Ching, the foundational text of Taoism, begins with a meditation on the Wu, the unnameable formless void that is, paradoxically, the mother of the 10,000 things, the entirety of the manifest world. It is a remarkable convergence of thought that these ancient, intuitive cosmologies, born from deep introspection, seem to be pointing towards the same fundamental truth that modern physics is now uncovering through the rigorous language of mathematics and experimentation. Quantum mechanics, that strange and wonderful pillar of modern science, has given us a new language to describe this creative void. It tells us that even in a perfect vacuum, a space cooled to absolute zero and shielded from all external influence, there is an incessant, irreducible quantum jiggle. This is the world of quantum fluctuations, a place where pairs of virtual particles and their antimatter counterparts are constantly bubbling into existence, borrowing a tiny amount of energy from the vacuum for an immeasurably short time before annihilating each other and returning their borrowed energy to the void. This is not a theoretical fantasy. It is a direct consequence of one of the most fundamental principles of nature, Werner Heisenberg's uncertainty principle. Formulated in 1927, this principle states that there is an irreducible trade-off in our knowledge of certain pairs of properties of a quantum system. The more precisely you know a particle's position, the less precisely you can know its momentum. This fundamental uncertainty means that no region of space can ever be truly, definitively empty. The very act of measuring a region to confirm its emptiness would, by the uncertainty principle, inject energy into it. At the most fundamental level, there is no such thing as a truly empty or static space. Every point in the cosmos is permeated by a web of quantum fields, one for each type of fundamental particle. These fields are never completely at rest. They are always vibrating, always fluctuating, even in their lowest energy state. This irreducible minimum energy of the vacuum is known as zero-point energy. It is the baseline hum of the universe, the silent, ever-present music of the void. And this is not just a mathematical abstraction. The physical effects of these virtual particles and their zero-point energy can be measured. The Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948 and later confirmed experimentally, shows that two uncharged parallel metal plates placed very close together in a vacuum will be pushed together by an invisible force. This force is not gravity, nor electromagnetism. It is the pressure of the quantum vacuum itself. The space between the plates can only accommodate virtual particles of certain wavelengths, while the space outside the plates can accommodate all wavelengths. This creates a pressure differential, a net force pushing the plates together. The void itself can exert a physical force. It is a stunning, tangible demonstration that what we call emptiness is, in fact, a dynamic, energetic, and powerful medium. The creative potential of this quantum vacuum is not limited to the fleeting dance of virtual particles. It may be the very source of our entire universe. The theory of cosmic inflation, one of the cornerstones of modern cosmology, proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated, exponential expansion. The driving force behind this inflation is thought to have been the energy of a quantum field, known as the inflaton field, trapped in a high-energy, the false vacuum state. As this field relaxed to its true lower energy state, it released its stored energy, flooding the nascent universe with the matter and radiation we see today. In this picture, the universe is a kind of macroscopic quantum fluctuation, a bubble of reality that was inflated to cosmic proportions by the energy of the void. This idea leads to an even more mind-boggling possibility, the quantum foam. First envisioned by the physicist John Wheeler, this is the idea that at the smallest possible scales of distance, the so-called Planck length, an unimaginably small 10 to the power of minus 35 meters, the very fabric of space-time is not smooth and continuous, but a chaotic, turbulent foam of microscopic black holes and wormholes, constantly being created and annihilated by quantum fluctuations. At this fundamental level, our familiar notions of space and time break down. This is the realm of quantum gravity, the yet-to-be-discovered theory that will unify Einstein's general relativity with quantum mechanics. In this foamy quantum reality, a sufficiently large fluctuation could, in principle, give rise to a new, expanding universe. Our cosmos could be a single, fortunate bubble that emerged from this infinite, eternal sea of quantum potential. This is the scientific version of a universe from nothing, a concept explored by physicist Lawrence Krauss. The nothing in this context is not an absolute philosophical void, but the rich, dynamic, and endlessly creative quantum vacuum. This completely inverts our classical understanding of reality. We no longer see the void as a passive, empty stage upon which the cosmic drama unfolds. We see the void itself as the primary actor, the generative source, the mother of all that is. The emptiness between the stars is not an absence. It is the presence of an infinite potential, a potential that, some 13.8 billion years ago, blossomed into the vast, complex, and beautiful universe we call home. And so, as you lie in the quiet of the night, as your consciousness begins to drift into the silent, inner space of sleep, you are, in a sense, returning to this primordial state. You are entering your own personal quantum vacuum, a space of pure potential, a space where new thoughts, new dreams, and new realities can be born from the creative silence of your own being. In the early 1980s, the standard Big Bang model, while remarkably successful in describing the evolution of the universe from a hot, dense state, was facing a series of deep, conceptual puzzles. It was like having a perfectly working car, but with no idea how the engine was built or why it had started in the first place. Then, on a cold December night in 1979, a young American physicist named Alan Guth, poring over his equations, had what he later called spectacular realization. He had stumbled upon the cosmic ignition key. The theory he conceived that night, the theory of cosmic inflation, would not just solve the lingering puzzles of the Big Bang, it would fundamentally reshape our understanding of the first, infinitesimal moments of creation, and it would do so by unleashing the immense creative power of the quantum vacuum. The story that inflation tells is one of almost unimaginable drama. It proposes that in the very first flicker of time, between roughly 10 to the power of minus 36 and 10 to the power of minus 32 seconds after the Big Bang, the universe underwent a period of astonishing, hyper-accelerated, exponential expansion. It was a cosmic growth spurt of truly epic proportions. During this fleeting, almost timeless instant, the size of the universe increased by a factor of at least 10 to the power of 26, a number so large it is difficult to represent with analogies. It is like taking an object smaller than a single proton and stretching it to the size of a grapefruit in a time far shorter than it takes light to cross that same proton. This is not just an expansion in space, it is an expansion of space itself, a stretching of the very fabric of reality at a rate that completely dwarfs the speed of light. The engine that powered this explosive growth, according to inflationary theory, was the energy of a quantum field, dubbed the inflaton field, which was momentarily trapped in a high-energy, unstable state known as a false vacuum. Imagine a ball perched precariously in a small divot at the very peak of a vast, steep hill. It possesses a huge amount of potential energy, and it is in a state of metastable equilibrium. A tiny quantum jiggle is all it would take to send it cascading down the hill, releasing its stored potential energy as the kinetic energy of motion. The false vacuum of the early universe was like this ball at the top of the hill. It was a state of incredibly high and uniform energy density, and this energy had a peculiar and powerful property. It exerted a strong negative pressure, which, according to Einstein's theory of general relativity, creates a powerful gravitational repulsion. It was this anti-gravity of the false vacuum that drove the exponential, inflationary expansion. Eventually, this false vacuum state decayed, like the ball rolling down the hill, into the true, lower energy vacuum state of our current universe. This process, called reheating, was a cataclysmic event. The immense energy that had been stored in the inflaton field was released, flooding the now vast, empty universe with a hot, dense, and uniform soup of fundamental particles and radiation. This is the starting point of the standard, hot Big Bang model. Inflation, in this sense, is not an alternative to the Big Bang. It is a prequel, a brilliant and necessary prologue that sets the stage and explains the seemingly miraculous initial conditions from which the rest of cosmic history unfolded. The true elegance of inflationary theory lies not just in its dramatic narrative, but in its remarkable ability to solve the deep, conceptual puzzles that had plagued the standard Big Bang model. One of the most profound of these was the horizon problem. When we observe the cosmic microwave background CMB, the faint, relic radiation from the infant universe, we find that it has an almost perfectly uniform temperature in all directions, to an accuracy of about 1 part in 100,000. This is a profound mystery. In the standard Big Bang model without inflation, regions of the sky that are on opposite horizons today were never in causal contact with each other. They were too far apart for light, or any other signal, to have traveled between them in the time since the beginning of the universe. So, how could they have possibly reached the same temperature? It is as if you walked into a vast, cavernous room and found that the temperature at every single point was identical to within a tiny fraction of a degree. without any heating or cooling system to have ever been turned on. Inflation provides a beautifully simple solution. Before the period of exponential expansion, the region of space that would eventually become our entire observable universe was an incredibly tiny, subatomic patch. It was so small that it was in perfect causal contact with itself. There was plenty of time for all parts of this patch to interact, to exchange energy, and to reach a state of thermal equilibrium, a state of uniform temperature. Inflation then took this tiny, smooth, and causally connected region and stretched it to astronomical proportions in the blink of an eye. The uniformity was preserved, locked into the expanding fabric of space, creating the smooth, isotropic universe we see today. The second major puzzle solved by inflation is the flatness problem. General relativity tells us that the geometry of spacetime is determined by its total density of matter and energy. If this density is above a certain critical value, the universe will be closed, like the surface of a sphere, and will eventually collapse. If it is below the critical value, the universe will be open, like the surface of a saddle, and will expand forever. The flat universe of Euclidean geometry is a special knife-edge case, corresponding to a density that is exactly equal to the critical density. Our observations tell us that our universe is astonishingly, exquisitely flat. For this to be the case, the initial density of the universe at the time of the Big Bang would have had to be fine-tuned to a degree of precision that is almost beyond comprehension, about 1 part in 10 to the power of 60. This seems like an absurdly improbable coincidence. Inflation solves this problem in a natural and elegant way. Any initial curvature that the universe may have had, whether positive or negative, would have been stretched out and flattened by the immense exponential expansion. In the same way that inflating a small, wrinkled balloon to the size of the Earth would make its surface appear perfectly flat to an observer on it. Inflation drives the geometry of the universe so close to perfect flatness that it is, for all practical purposes, indistinguishable from it. But inflation does more than just solve old problems. It makes a remarkable and testable prediction. The theory states that the tiny, unavoidable quantum fluctuations as in the inflaton field itself during the period of inflation would not have been smoothed out. Instead, they would have been stretched to macroscopic and even astronomical scales. These stretched-in-time quantum fluctuations would have become the seeds of cosmic structure, the tiny variations in density that, over billions of years, and would grow under the influence of gravity to become all the galaxies, the clusters of galaxies, and the vast cosmic web that we see today. The specific statistical properties of these primordial fluctuations, their near, but not perfect, scale invariants are a unique fingerprint of inflation, and they have been confirmed with stunning precision by our detailed maps of the cosmic microwave background. We are, in the most literal and profound sense, the children of quantum fluctuations. Our entire cosmic home, with all its grandeur and complexity, is a macroscopic fossil of the inherent uncertainty of the primordial quantum void, a void that was momentarily supercharged with an incredible inflationary energy. The theory of inflation, in its more modern and sophisticated forms, has led to a concept that is even more profound and mind-altering than the Big Bang itself: the idea of eternal inflation and the multiverse. The Russian-American cosmologist Andrei Linde, one of the key architects of modern inflationary theory, realized that the process of inflation, once started, may be very difficult to stop. In his model of chaotic inflation, the inflaton field is not a single uniform entity, but a field that has different random values in different regions of the primordial universe. In some regions, the field will quickly roll down its potential hill. Inflation will end, and a bubble universe like ours will be born in a hot Big Bang. But in other regions, quantum fluctuations can kick the field up the hill, causing inflation to continue, and even to become a self-reproducing eternal process. In this scenario, the end of inflation in our region was just a local event. The larger meta-universe, the inflationary sea, is still out there, expanding at an incredible rate and constantly spawning new bubble universes. The Big Bang was not a singular, unique event in the history of time. It is a common, ongoing process in the vast, eternal landscape of the multiverse. This is a vision of reality that is almost impossible to fully comprehend. Our entire observable universe, with its hundreds of billions of galaxies, is just one bubble in an infinite, bubbling foam of other universes. And these other universes may not be like our own. The decay of the inflaton field in each bubble could lead to different vacuum states, resulting in different fundamental particles, different forces of nature, different physical laws. There could be universes with 2 dimensions of space, or 10. Universes where gravity is a repulsive force, or where the speed of light is different. Most of these universes would be sterile, bizarre, and inhospitable wastelands, incapable of supporting any form of complexity or life. But in an infinite multiverse, even the most improbable events become not just possible, but inevitable. The existence of a universe like ours, with its specific and seemingly fine-tuned set of physical constants that allow for the formation of stars, planets, and conscious observers, is no longer a miracle to be explained. It becomes a simple selection effect. We find ourselves in a universe that is hospitable to life for the same reason that we find ourselves living on a planet with liquid water and a breathable atmosphere. We could not exist to ask the question in any of the other, far more numerous, inhospitable environments. The multiverse, in this sense, provides a scientific, albeit untestable, explanation for the anthropic principle. The idea of eternal inflation and the multiverse is on the cutting edge of theoretical physics, and it is by no means universally accepted. Critics point out that it is, by its very nature, unobservable, and therefore may not be a truly scientific theory. But its proponents argue that it is a natural and almost unavoidable consequence of combining our best theories of cosmology and quantum field theory. And there may be ways to search for indirect circumstantial evidence. If our bubble universe had, in its distant past, collided with another bubble, it might have left a bruise on our cosmos, a specific circular pattern of temperature fluctuations in the cosmic microwave background. The search for such a cosmic scar is an active, if long shot, area of research. Whether the multiverse is a physical reality or a beautiful mathematical dream, the theory of inflation has fundamentally and irrevocably changed our view of our own origins. It has taken the Big Bang from a mysterious, unexplained singularity and placed it within a larger, dynamic, and potentially eternal cosmic context. It has shown us how the grand, macroscopic structure of our universe can be born from the subtle, microscopic quantum fluctuations of the void. And it has opened our minds to the breathtaking possibility that our entire cosmos is just a single, fleeting note in an infinite and eternal cosmic symphony. The concept of the Big Bang itself, the central event in our cosmic story, is one that is often shrouded in misconception. The popular image is that of a gigantic firework, a singular explosion happening at a specific point in a pre-existing empty space. But this picture is fundamentally wrong. The Big Bang was not an explosion in space. It was an explosion of space. It was not an event that happened at a particular location. It was an event that happened everywhere at once. To grasp this counterintuitive idea, the analogy of an expanding balloon is helpful. If you imagine our three-dimensional space as the two-dimensional surface of a balloon, and you draw a number of dots on this surface to represent galaxies, then as you inflate the balloon, you will see that every dot is moving away from every other dot. An observer on any given dot would see all the other dots receding from them, and the further away a dot is, the faster it would appear to be moving away. There is no center to this expansion on the surface of the balloon. The expansion is happening everywhere. The fabric of the balloon itself is stretching. In the same way, the expansion of the universe is a stretching of the fabric of space-time. Every point in our current universe, including the point where you are right now, was part of that initial, infinitely hot and dense state. The Big Bang happened right here and everywhere else. This is a direct consequence of Einstein's general theory of relativity, which describes space and time not as a static, absolute background, but as a dynamic, physical entity that can be bent, warped, and stretched by the presence of matter and energy. The Big Bang, then, is not a theory of the origin of the universe from nothing. It is a theory of the evolution of the universe from a very hot, dense, and rapidly expanding initial state. It does not, in its standard form, address the question of what caused the Big Bang, or what, if anything, came before it. Those are questions that lie beyond the domain of the theory, in the realm of quantum gravity and the speculative cosmologies we have discussed. The story that the Big Bang does tell is the story of the first 14 billion years of our universe's life, a story of cooling, of expansion, and of the gradual emergence of complexity from a state of primordial simplicity. In the first fractions of a second, the universe was an unimaginably hot and dense soup of fundamental particles, quarks, leptons, and the force-carrying bosons, a state known as a quark-gluon plasma. As the universe expanded and cooled, this plasma froze out. After about 1 microsecond, the quarks bound together to form the protons and neutrons that make up the nuclei of atoms. For the next few minutes, in a process known as Big Bang nucleosynthesis, these protons and neutrons fuse together to form the nuclei of the lightest elements, mostly hydrogen and helium, with trace amounts of lithium. The universe was still a hot, dense, and opaque plasma. The temperature was so high that electrons were not bound to the atomic nuclei. This sea of free electrons acted like a dense fog, constantly scattering photons of light, preventing them from traveling any significant distance. The universe was dark, not because there was no light, but because the light was trapped. This period lasted for about 380,000 years. Then, as the universe continued to expand and cool, it reached a critical temperature of about 3,000 Kelvin. At this point, the electrons had slowed down enough to be captured by the atomic nuclei, forming the first stable, neutral atoms. This event is known as recombination. Suddenly, the fog lifted. The universe became transparent to light. The photons that were present at that time were now free to travel unimpeded through space, and they have been traveling ever since. Their wavelengths stretched by the subsequent expansion of the universe from high-energy visible light into the cool, faint microwaves that we detect today. This is the cosmic microwave background, the oldest light in the universe, a beautiful, uniform glow that comes to us from all directions in the sky. It is a baby picture of our universe, a snapshot of the moment it first became transparent. A fossil that carries with it a wealth of information about the conditions of the early cosmos. The story of the Big Bang is a story of transformation, a story of how, from a state of almost perfect uniformity and simplicity, all the rich and complex structures we see today, the stars, the galaxies, the planets, and ourselves, were gradually born. It is a story that is written in the light of the distant stars, in the composition of the elements, and in the faint, ancient glow of the cosmic microwave background. It is our story. As our journey through the cosmos brings us closer to the present day, we encounter the universe's most profound and perplexing mystery, the existence of dark energy. This is not a subtle theoretical curiosity. It is the dominant component of our universe, making up roughly 68% of its total energy density. It is the invisible, silent force that is shaping the ultimate destiny of our cosmos, and we have almost no idea what it is. The discovery of dark energy in 1998 was a complete surprise. Two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using Type Ia supernovae as standard candles to measure the expansion rate of the universe at different times in its history. A Type Ia supernova is the thermonuclear explosion of a white dwarf star, and it always has the same intrinsic brightness, making it a perfect cosmic yardstick. The teams expected to find that the expansion of the universe was slowing down, as the mutual gravitational attraction of all the matter in the cosmos should be acting as a brake. To their astonishment, they found the exact opposite. The distant supernovae were dimmer than expected, which meant they were further away than they should have been if the expansion was slowing down. The expansion of the universe is accelerating. This groundbreaking discovery, which earned its leaders the 2011 Nobel Prize in Physics, implied the existence of a new, previously unknown form of energy with a strange and powerful property, a strong negative pressure that acts as a form of cosmic anti-gravity, pushing space-time apart. This is what we call dark energy. The simplest and most natural candidate for dark energy is the energy of the quantum vacuum itself, the zero-point energy we discussed earlier. In the context of Einstein's general relativity, a constant vacuum energy density would manifest as a cosmological constant, a term that Einstein himself had introduced into his equations in 1917, only to later retract it as his biggest blunder when Edwin Hubble discovered the universe was expanding. In a beautiful historical irony, modern cosmology has resurrected Einstein's blunder and made it the centerpiece of our standard cosmological model. A universe dominated by a cosmological constant has a strange and counterintuitive property. As space expands, the density of matter and radiation decreases, as they are spread out over a larger volume, but the density of vacuum energy remains constant. This means that as the universe gets bigger, the total amount of dark energy increases. It is as if new energy is being created from the expanding space itself. In the early universe, when the density of matter and radiation was very high, the effects of dark energy were negligible. But as the universe expanded and thinned out, dark energy gradually became the dominant component. It took over from gravity as the primary driver of cosmic evolution about 5 billion years ago, and it has been accelerating the expansion ever since. The problem, as we have seen, is the vacuum catastrophe. The theoretical value of the vacuum energy calculated from quantum field theory is an absurd 120 orders of magnitude larger than the observed value of dark energy. This colossal discrepancy has led many physicists to believe that the simple identification of dark energy with vacuum energy must be wrong. This has led to a host of alternative theories. Perhaps dark energy is not a constant, but is a dynamic entity, a new quantum field dubbed quintessence that is slowly rolling towards its minimum energy state. In this scenario, the rate of cosmic acceleration could change over time, leading to a different ultimate fate for the universe. Or perhaps our understanding of gravity is wrong. Maybe general relativity needs to be modified on cosmological scales. These modified gravity theories attempt to explain the accelerated expansion without invoking any new form of energy. They propose that gravity itself becomes repulsive on very large distances. Distinguishing between these different possibilities is one of the primary goals of modern cosmology. Observatories like the Euclid Space Telescope and the Vera C. Rubin Observatory are designed to map the distribution of galaxies and the history of cosmic expansion with unprecedented precision, which will allow us to measure the properties of dark energy and to test whether it has changed over time. The nature of dark energy is not just a question for physicists. It is a question that touches on the ultimate fate of our universe. A universe dominated by a constant dark energy is destined for a big freeze. A universe dominated by a phantom energy that grows stronger over time is destined for a big rip. And a universe where dark energy could one day decay or change its sign could be destined for a big crunch. We live in a universe whose destiny is being written by an invisible, mysterious, and powerful force. A force whose true nature remains one of the greatest and most profound challenges in all of science. The empty space that surrounds us is not empty at all. It is a dynamic, energetic, and powerful entity. A cosmic protagonist whose story we are only just beginning to understand. The idea that our universe might not be the only one, that it could be part of a vast, perhaps infinite, multiverse, is a concept that has migrated from the realms of science fiction and philosophy into the heart of modern theoretical physics. It is a breathtaking and humbling idea, one that, if true, would represent the final and most profound step in the Copernican revolution. The long historical process of decentering humanity from a privileged position in the cosmos. The concept of the multiverse is not a single, coherent theory, but rather a consequence of several of our most ambitious and successful physical theories. We have already encountered one of its most compelling sources, the theory of eternal cosmic inflation. In this picture, our universe is just one bubble that formed when a small patch of an eternally inflating meta-universe decayed into a lower energy state. Other bubbles are constantly forming, each potentially with different physical laws, constants, and even different numbers of dimensions. This creates a vast, level 2 multiverse of disconnected, parallel realities. Another powerful argument for the multiverse comes from the many worlds interpretation of quantum mechanics. As we discussed, this interpretation, first proposed by Hugh Everett, solves the measurement problem by positing that the wave function never collapses. Instead, every quantum measurement causes the universe to split into multiple branches, with each branch corresponding to one of the possible outcomes. This creates a level 3 multiverse, a constantly branching tree of parallel realities. In this multiverse, there are an infinite number of yous, each living out the consequences of a different quantum outcome. There is a version of you who is reading this, and a version of you who decided to go for a walk instead. Every possibility is realized somewhere in this vast quantum multiverse. A third and more straightforward type of multiverse is the level 1 multiverse. This is simply the idea that our observable universe, the region of space from which light has had time to reach us since the Big Bang, is just a small patch of a much larger and possibly infinite universe. If space is infinite, then in that infinite volume, every possible configuration of matter and energy must, by statistical necessity, repeat itself an infinite number of times. This means that somewhere out there, far beyond our cosmic horizon, there is another galaxy, another solar system, another Earth, and another you, an identical copy living out an identical life. And there are an infinite number of such copies. This is a staggering and deeply unsettling thought, one that challenges our sense of individuality and uniqueness. Finally, there is the most abstract and philosophical type of multiverse, the level 4 or mathematical universe, proposed by physicist Max Tegmark. This is the idea that physical reality is, at its core, a mathematical structure. And since all consistent mathematical structures exist in a timeless, Platonic sense, then all possible mathematical structures exist as physical realities. Our universe is just one, particularly complex, mathematical structure, one that happens to have the right properties to allow for the emergence of self-aware substructures, like us, who can contemplate the mathematical nature of their own existence. The multiverse, in all its forms, provides a powerful, if controversial, framework for addressing the fine-tuning problem. The fact that the physical constants of our universe seem to be so exquisitely tuned to allow for the existence of life is no longer a miracle that requires a supernatural explanation. It is a simple selection effect. We find ourselves in a universe that is hospitable to life because it is the only kind of universe we could find ourselves in. We are the survivors of a cosmic lottery of unimaginable proportions. The primary criticism of all multiverse theories is that they are, by their very nature, untestable. We can never travel to another bubble universe or communicate with a parallel branch of the quantum wave function. This has led some to argue that the multiverse is not a scientific theory, but a metaphysical one. But its proponents argue that the theories from which the multiverse arises, like inflation and quantum mechanics, are themselves highly testable. If these theories continue to pass every experimental test we throw at them, then we may be forced to take their more bizarre consequences, like the multiverse, seriously, and there may be indirect, circumstantial ways to search for evidence. The cosmic bruise from a collision with another bubble universe is one such possibility. The search for a variation in the fundamental constants of nature across the sky is another. Whether the multiverse is a physical reality or not, the very fact that it is a serious topic of discussion among many of the world's leading physicists is a testament to how far our cosmic horizons have expanded. It is a concept that forces us to confront the true scale of reality, to question our most basic assumptions about our own uniqueness, and to embrace a vision of the cosmos that is infinitely richer, stranger, and more magnificent than we ever dared to imagine. As we gaze out into the cosmos, our vision is fundamentally limited. The night sky appears as a vast dark dome, but this is an illusion. We are not looking out at a static three-dimensional space. We are looking back in time. The light from the moon takes a little over a second to reach us, so we see it as it was a second ago. The light from the sun takes 8 minutes. The light from our nearest stellar neighbor, Proxima Centauri, takes over 4 years. And the light from the Andromeda Galaxy, our closest major galactic neighbor, has been traveling for 2.5 million years. When we look at the most distant galaxies visible in the James Webb Space Telescope, we are seeing them as they were over 13 billion years ago. When the universe was just a toddler, this intimate connection between distance and time defines our cosmic horizon. Because the universe has a finite age of approximately 13.8 billion years, and because light travels at a finite speed, there is a fundamental limit to how far we can see. The boundary of our observable universe is not a physical wall, but a temporal one. It is the distance from which light has had just enough time to reach us since the Big Bang. We can never, even in principle, see what lies beyond this horizon. The universe may be infinite, but our view of it is finite. The situation is made even more profound by the accelerating expansion of the universe. Not only is there a horizon that limits our view of the past, but there is also an event horizon that limits our view of the future, because space itself is expanding, and this expansion is accelerating. Distant galaxies are receding from us at ever-increasing speeds. There is a critical distance beyond which galaxies are receding from us faster than the speed of light. This does not violate Einstein's theory of relativity, as it is space itself that is expanding, not the galaxies moving through space. But it does mean that any light emitted by those galaxies after they cross this event horizon will never be able to reach us. They will be causally disconnected from our future. They will, in a sense, disappear from our universe. The night sky of the far future will be a profoundly lonely place. As more and more galaxies recede beyond our event horizon, the cosmic landscape will become increasingly empty. Eventually, only the members of our own gravitationally bound local group of galaxies will remain visible. A future civilization, looking up at the sky, might conclude that they live in a single island universe, forever unaware of the vast cosmic ocean that we are privileged to still be able to see. This concept of an event horizon, a one-way membrane that separates the observable from the unobservable, is most famously associated with black holes. A black hole is a region of space-time where gravity is so intense that nothing, not even light, can escape. Its event horizon is the point of no return. Any object or any information that crosses this boundary is seemingly lost to the outside universe forever. In the 1970s, Stephen Hawking revolutionized our understanding of black holes by showing that they are not completely black. Due to quantum effects at the event horizon, the constant creation and annihilation of virtual particle pairs from the quantum vacuum black holes should slowly emit a faint thermal radiation. This Hawking radiation causes the black hole to lose mass and, over immense timescales, to eventually evaporate completely. This brilliant discovery, which elegantly weaves together the principles of general relativity, quantum mechanics, and thermodynamics, also gave rise to one of the deepest paradoxes in modern physics, the black hole information paradox. According to the fundamental principles of quantum mechanics, information can never be destroyed. The total amount of information in a closed system must always be conserved. But if you throw an encyclopedia, with all its rich and complex information, into a black hole, that information seems to be lost forever behind the event horizon. And when the black hole evaporates, the Hawking radiation it emits appears to be purely thermal and random, containing no memory of the information that fell in. So, where did the information go? Is it truly destroyed, in violation of one of the most sacred principles of physics, or does it somehow escape, subtly encoded in the quantum correlations of the outgoing radiation? This paradox has been a major driver of research in theoretical physics for decades, and its resolution is thought to be a key step towards a full theory of quantum gravity. Recent theoretical work has suggested that the information is not lost, but is preserved on the event horizon itself, a concept related to the holographic principle, which posits that all the information in a three-dimensional volume of space can be encoded on its two-dimensional boundary. The existence of horizons, both cosmological and black hole, is a profound and humbling feature of our universe. It tells us that there are fundamental, built-in limits to our knowledge. There are parts of the cosmos and aspects of nature that may forever lie beyond the reach of our direct observation. But they are also a powerful spur to our theoretical imagination, forcing us to devise new and creative ways to understand the realities that are hidden from our view. They are a reminder that the universe is not a transparent, open book, but a deep and multi-layered mystery. A mystery whose most profound secrets are often hidden right at the very edge of what we can see. The grand narrative of our cosmos, as told by the standard Big Bang model, is a linear one. It is a story with a definite beginning, a long period of evolution, and a potential final end. But is this the only possible story? Could the universe be a more timeless, more cyclical entity, an eternal dance of creation and destruction, with no absolute beginning or end? This idea of a cyclic universe is one of the oldest and most enduring in human thought. It is found in the concept of the kalpas in Hindu cosmology, vast time cycles of cosmic creation, maintenance, and dissolution. It is present in the philosophy of the ancient Stoics, with their idea of a great year, at the end of which the universe is consumed by fire and then reborn. And it is a concept that has been given a new, scientific life in some of the most advanced and speculative theories of modern cosmology. One of the most well-developed of these is the ekpyrotic or cyclic model, proposed by physicists Paul Steinhardt and Neil Turok. This model is rooted in the ideas of string theory and extra dimensions. It envisions our universe as a three-dimensional brane, or membrane, floating in a higher dimensional space, or bulk. There is another, parallel brane nearby. In this picture, the Big Bang is not the beginning of time, but is the result of a gentle, periodic collision between our brane and this other brane. Each collision releases a tremendous amount of energy, which is converted into the hot, dense matter and radiation of a new cosmic cycle. After the collision, the branes bounce apart, and our universe expands and cools, allowing for the formation of galaxies, stars, and planets. But this expansion is not destined to continue forever. A form of dark energy. In this model, a potential energy between the branes eventually causes the expansion to slow down and the branes to begin to move back towards each other, drawn together by a spring-like force. This leads, after a period of slow contraction, to another gentle collision, another Big Bang, and the beginning of a new cycle. Each of these cycles could last for 1 trillion years or more, an almost unimaginable timescale from a human perspective, but just a single beat in the eternal rhythm of the cosmos. This cyclic model has several attractive features. It elegantly solves the horizon and flatness problems of the standard Big Bang model without the need for a period of cosmic inflation. The smoothness of our universe is a result of the long period of slow contraction before the last bang, which had plenty of time to smooth out any irregularities. It also provides a natural explanation for dark energy as the force that drives the cycles. And most profoundly, it eliminates the need for an initial singularity, the point of infinite density and temperature where the laws of physics break down. In a cyclic universe, there is no absolute beginning. The universe has always existed and will always exist in an endless sequence of cosmic epochs. However, the cyclic model is not without its challenges. The physics of the brane collision, the bounce from a contracting phase to an expanding one, is incredibly complex and requires a full, and as yet unknown, theory of quantum gravity to be described accurately. And the model must also contend with the second law of thermodynamics. If entropy or disorder increases with each cycle, how can the universe return to the same low entropy state at the beginning of each new cycle? The proponents of the model argue that the vast expansion that occurs during each cycle so dilutes the entropy that it becomes negligible, effectively resetting the cosmic clock. Another related idea is the conformal cyclic cosmology (CCC) proposed by the eminent physicist Roger Penrose. In this model, the universe does not bounce, but expands forever. However, Penrose argues that in the very far future of our universe, after all the black holes have evaporated and only a cold, thin gas of photons and other massless particles remains, the universe loses its sense of scale. In this state, the infinitely large and cold future of our eon becomes mathematically equivalent, via a conformal transformation, to the hot, dense, low entropy state of a Big Bang for a new eon. The end of one universe becomes the beginning of the next. The cyclic models, in all their forms, offer a radically different vision of our cosmic story. They replace the linear, one-off narrative of the standard Big Bang with a more timeless, more eternal, and perhaps more philosophically satisfying picture of a universe that is constantly renewing and reinventing itself. While still a minority view among cosmologists, the idea of a cyclic universe is a powerful reminder that our current understanding is still provisional, and that the ultimate truth about our cosmic origins may be far stranger and far more beautiful than we can yet imagine. The apparent, exquisite fine-tuning of the fundamental constants of nature to allow for the existence of life is one of the most profound and philosophically charged mysteries in all of science. It is a puzzle that seems to hint at something deeper, something beyond the standard, materialistic worldview. Why is the strength of gravity just right to allow for long-lived stars? Why is the mass of the neutron just slightly heavier than the mass of the proton? A delicate balance that allows for the stability of atomic nuclei. Why is the cosmological constant so incredibly, exquisitely small, allowing for the formation of galaxies? This fine-tuning problem has led to the formulation of the anthropic principle, a controversial but powerful idea that attempts to explain this cosmic coincidence by invoking our own existence as observers. The weak anthropic principle is a relatively straightforward and almost tautological statement. It simply says that the conditions we observe in the universe must be compatible with the existence of observers. It is a form of selection bias. We find ourselves in a universe that is suitable for life because we could not have found ourselves in one that wasn't. It is a valid, but not particularly explanatory, principle. The strong anthropic principle, however, makes a much bolder and more metaphysical claim. It suggests that the universe is, in some sense, compelled to have properties that allow for the emergence of life and consciousness. This can be interpreted in several ways, from the theological, a divine designer, to the teleological, a cosmic purpose. The anthropic principle, in its weak form, finds a natural and scientific home in the context of the multiverse. If our universe is just one of a vast, perhaps infinite, ensemble of other universes, each with its own randomly assigned set of physical constants, then the fine-tuning problem dissolves. It is no longer a miracle that we find ourselves in a life-friendly universe. It is a statistical inevitability. We are simply living in one of the rare, habitable oases in a vast, sterile cosmic desert. This is a powerful and elegant explanation, but it relies on the existence of unobservable parallel realities. But is there a way to have a single, self-consistent universe without resorting to either a multiverse or a divine designer? This is the idea behind the bootstrap picture of the universe, a concept that has been a recurring dream in theoretical physics. The bootstrap hypothesis, in its most ambitious form, suggests that the universe is a completely self-consistent and unique whole. There is only one possible way for the universe to be. The values of the fundamental constants, the properties of the particles, the laws of physics themselves, are not accidental or random. They are all fixed by the requirement of overall mathematical and logical consistency. The universe, in a sense, pulls itself up by its own bootstraps. It is the way it is because it is the only way it could be. This is a vision of a universe that is not just described by mathematics, but is governed by a deep, underlying logical necessity. In this picture, there is no need for an anthropic principle to explain fine-tuning, because there is nothing to fine-tune. The constants have the values they do for the same reason that the ratio of a circle's circumference to its diameter is pi. It is a mathematical truth. The bootstrap dream was particularly popular in the 1960s in the context of the strong nuclear force, but it fell out of favor with the rise of the Standard Model, which seemed to have a number of arbitrary free parameters. However, the dream has not entirely died. The quest for a final, unified theory of everything, like string theory, is, in a sense, a quest for a bootstrap explanation. The hope is that a final theory will have no free parameters, that it will uniquely determine all the properties of our universe from a single, elegant set of principles. In the absence of such a final theory, the anthropic principle can be seen as a kind of poor man's bootstrap. It is a way of relating the properties of the universe to our own existence, a partial and existential form of self-consistency. When we observe a wild flower, we are also observing the universe that gave rise to it, a universe with the right chemistry, the right stellar evolution, the right physical laws. The organism and its universe are a self-consistent whole. The hope is that one day, our understanding will be so complete that when we observe a single electron, we will be able to deduce the properties of the entire universe from the requirement of self-consistency. We will find, as the poet William Blake wrote, a world in a grain of sand and a heaven in a wild flower. And the debate between the anthropic, multiverse picture and the bootstrap, unique universe picture is a debate about the very nature of physical law. Are the laws of nature contingent, accidental, and just one of a vast number of possibilities, or are they necessary, unique, and fixed by a deep, underlying logic? It is a debate about chance versus necessity at the most fundamental level of reality, and it is a debate that is far from being resolved. The quest to understand the universe inevitably leads us back to a profound and perplexing riddle, a riddle that lies at the very heart of the relationship between the knower and the known. It is the containment riddle where, in a universe, is the cosmologist who is studying that universe. This is not a trivial semantic puzzle. It is a deep, epistemological problem that challenges the very foundations of our scientific worldview. All other scientists can, to some extent, avoid this riddle. The biologist studies an organism, but she is not that organism. The geologist studies a rock, but he is not that rock. They can maintain a sense of objective distance, of an observer who is separate from the system being observed, but the cosmologist studies the entire universe, and she is undeniably a part of that universe. She is a product of the very cosmic evolution she seeks to understand. Her consciousness, her thoughts, her theories are all phenomena within the universe. How, then, can a part contain a picture of the whole that includes the part itself? This is a problem that has been recognized by thinkers for centuries. The philosopher and scientist Erwin Schrödinger, in his book Mind and Matter, pointed to this fundamental paradox. He noted that in order to create an objective, scientific picture of the world, we have, by necessity, excluded the subject of cognition from the domain of nature we seek to understand. We have stepped back and adopted the role of a non-concerned observer, and in doing so, we have created an objective world that does not, and cannot, contain the very consciousness that is doing the observing. The physical universe of our scientific theories contains our physical bodies, our brains, our neurons, but it does not contain our minds, our subjective experience, our awareness. The physical world of atoms and galaxies, governed by mathematical laws, is a brilliant and powerful construction, but it is a construction that is, by its very nature, incomplete. It is a map that does not contain the mapmaker. The containment riddle is a direct challenge to the philosophy of physicalism or materialism, the idea that life and mind are nothing more than the collective dance of atoms. That consciousness is fully contained within, and can be fully explained by, the physical universe. Those who hold this view often confuse the physical universe, which is a scientific model, a world picture, with the unknown universe, the totality of reality, which includes the mind that creates the picture. They mistake the mask for the face. The riddle forces us to confront the possibility that consciousness is not a phenomenon in the universe, but is, in some sense, co-extensive with it, or even primary to it. This is not to deny the immense success of the physical sciences. The physical universe is a powerful and useful model that allows us to understand how things work and to control our environment. But it is a model, an image, a story, and the storyteller, the image maker. The consciousness that weaves the facts and spins the ideas is not contained within the story. The answer to the containment riddle, then, is that we, the conscious, observing beings who create these universes of thought, do not live in our models. We live in the larger, unknown universe, the totality that includes both the physical world and the mind that knows it. Our scientific and philosophical models are our attempts to create a map of this territory, But the map can never be the territory itself. The physical universe contains the brain, but it is the mind that contains the physical universe. This is a subtle but profound shift in perspective. It suggests that an adequate cosmology, a true theory of everything, will not be complete until it can account for the existence of the cosmologist herself. It will require a new kind of science, a science that can bridge the gap between the third-person, objective description of the physical world and the first-person, subjective reality of conscious experience. It is a challenge that has haunted philosophy in various guises for centuries, from the self-referential paradoxes of epistemology to the dizzying, bottomless chasm of self-awareness described by the Danish student in Paul Müller's famous tale. And it is a challenge that now, in the age of modern cosmology, stares the physicist directly in the face. We are not just in the universe is in us. And any final theory that fails to account for this fundamental, paradoxical, and beautiful truth will be, at best, a brilliant, but ultimately incomplete, picture of reality. The physical universe, as described by our scientific theories, is a world of matter, energy, and natural laws. But what, precisely, is a natural law? Are the principles that govern the evolution of life, for example, as fundamental as the laws that govern the motion of the planets? Since the time of Charles Darwin, the theory of evolution by natural selection has been the cornerstone of modern biology. And yet, it has often been challenged as being unfounded speculation, a historical narrative that cannot be proven with the same rigor as a physical law like gravity. But this is a profound misunderstanding of the nature of science. The law of natural selection is as physical, as real, and as demonstrable as any other principle in science. The theory requires just three simple and observable components. First, an interbreeding population of organisms. Second, a source of variation among the members of that population, which we now know to be rooted in the random mutations of their genetic code. And third, a selective environment, a set of conditions that causes differential survival and reproduction. Those organisms whose variations happen to give them a slight advantage in a particular environment will be more likely to survive and to pass on their genes to the next generation. Over time, these advantageous traits will become more common in the population, and the species will change. It will adapt. It will evolve. This is not a speculation. It is a logical necessity. And we have overwhelming evidence for its effectiveness, not just in the fossil record, but in our everyday lives. The widespread use of antibiotics, for example, has created a powerful selective environment for bacteria. Those rare individual bacteria that happen to have a random mutation that confers resistance to an antibiotic will survive and reproduce, while their non-resistant cousins are wiped out. The result is the evolution of antibiotic-resistant superbugs, a direct and often dangerous demonstration of natural selection in action. The law of natural selection is a beautiful example of how simple, local, and random processes can, over time, give rise to immense complexity, order, and adaptation. It is a law that connects the microscopic world of genes to the macroscopic world of organisms and ecosystems. And it is a law that is deeply intertwined with the arrow of time. Evolution is a historical process, a one-way journey of increasing adaptation and complexity, a process that is only possible in a universe with a strong thermodynamic arrow of time. But is life itself, the very phenomenon that natural selection acts upon, something that is fully contained within the physical universe? This brings us back to the containment riddle. The biologists will tell us that life is a manifestation of complex, organized physical systems of cells and atoms. But this is a description of the how of life, not the what of life. It describes the physical vehicle, but not the subjective experience of being alive. The physical universe contains the physical representations of life, the wild flowers, the brains, the DNA. But does it contain the aliveness itself? The mystery of life, like the mystery of consciousness, seems to point to a reality that is not fully captured by our current physical models. It hints at a universe where the distinction between the living and the non-living, between the mental and the material, may not be as absolute as we assume. The law of natural selection is a physical law that operates on living systems, but the very existence of those living systems, with their strange and wonderful properties of self-organization, of metabolism, of awareness, remains one of the deepest and most beautiful mysteries of the cosmos. The boundaries of our universe, both in time and in space, pose some of the most profound and challenging questions in all of cosmology. We have spoken of the cosmic horizon, the limit of our observable universe. But what about the edges of time itself? A Big Bang universe, in its standard form, has a definite beginning, a time-like edge in the past. If this universe is destined to collapse back on itself in a big crunch, it will have two time-like edges, a beginning and an end. What is the nature of these cosmic boundaries? They are presumably not sharp, cliff-like edges, but are more likely to be regions where the very concepts of space and time, as we know them, break down. The orderly historical sequence of events that constitutes our classical, macroscopic world may dissolve into a chaotic, quantum, metrical foam at the beginning and the end of time. The truth is, we do not fully understand these time-like edges, perhaps because we do not fully understand the nature of time itself. Insofar as time is a physical dimension, a part of the physical universe, it seems logical to assume that it is contained within the universe and cannot extend outside of it. The question, what came before the Big Bang, is often dismissed as being meaningless, as before is a concept that requires the existence of time. But this is not necessarily the end of the story. There are ways in which we can talk sensibly about a before. If our universe is just one bubble in a larger, eternally inflating multiverse, then before our Big Bang, there was the inflating quantum vacuum of the meta-universe. If our universe is part of a cyclic model, then before our Big Bang, there was the contracting phase of a previous cosmic eon. And there is another, even more intriguing possibility, the idea of contained creation within a parent universe. Suppose that our universe is the offspring of another, pre-existing physical universe, reproduced either spontaneously through a quantum process, like the formation of a black hole, or perhaps, even more speculatively, deliberately, by a highly advanced intelligent life in the parent universe. In this scenario, we can meaningfully speak of what happened in the parent universe before the birth of our own. The physicist Joe Rosen has even shown that it is theoretically possible for such a system to be self-creating, a cosmic Ouroboros where Universe X creates Universe Y in its own time, and Universe Y in turn creates Universe X in its time. This distinguishes between contained creation, which is the emergence of a new thing at a specific time and place within a pre-existing space like the birth of a flower or a child, and uncontained creation, which is the timeless and placeless creation of the universe itself. The popular conception of the creation of the universe often mistakenly frames it as a contained creation, an event happening in a pre-existing void, which leads to the misguided question of what came before. A more sophisticated understanding sees the creation of the universe as an uncontained one, an event that brings time and space themselves into being. But the possibility of a parent universe reframes the question once again, suggesting that our universe's creation may have been a contained event within a larger, pre-existing reality. This is a concept that blurs the line between science, philosophy, and even theology. It is a testament to the fact that as our scientific understanding deepens, the questions we ask become more profound, more subtle, and more beautifully intertwined with the great, timeless mysteries of existence. The quest to build an adequate cosmology, a complete and satisfying picture of the universe, is inextricably linked to the quest to build an adequate philosophy of mind. The two are not separate endeavors, they are two sides of the same. Deep inquiry into the nature of reality. As the philosopher of science Edwin Burt wrote, a truly adequate cosmology will only be possible when we have a philosophy of mind that can satisfy both the behaviorist impulse to make the mind a material for experimental manipulation and exact measurement, and the idealist impulse to account for the startling difference between a universe without mind and a universe organized into a living, sensitive unity through mind. The human sciences, from psychology to sociology, currently face an impasse precisely because their central concept, the self, remains a deeply mysterious and transcendental entity, a concept that resists a purely materialistic explanation. At the roots of all our knowledge, from the most objective physics to the most subjective psychology, lies the containment riddle. This riddle, in its various guises, has haunted Western philosophy for centuries, and now it has come to haunt the foundations of physics itself. It is the riddle of the self-referential loop, of the system that tries to contain a complete description of itself. The physicist Leon Rosenfeld, a close collaborator of Niels Bohr, recounted how Bohr himself was deeply impressed by this problem, as it was expressed in Paul Müller's The Tale of a Danish Student. The student in the tale is tormented by epistemological paradoxes, by the fact that his mind divides itself into two persons, one who tries to fool the other, while a third, who is in fact the same as the other two, is filled with wonder at this confrontation. "I don't know which ego is the real one to stop at," the student laments, "for as soon as I stop at any of them, another ego stops at it. My head gets all in a whirl with dizziness as if I were peering down a bottomless chasm, and the end of my thinking is a horrible headache." This is the infinite regress of self-awareness, the mind that tries to observe itself, observing itself. It is the same infinite regress that confronts the painter who tries to paint a picture of his studio that includes himself painting the picture. And it is the same infinite regress that confronts the cosmologist who tries to create a physical model of the universe that includes the very consciousness that is creating the model. Erwin Schrödinger recognized this problem with profound clarity. "Without being aware of it," he wrote, "we exclude the subject of cognition from the domain of nature that we endeavor to understand. We step with our own person back into the part of an onlooker who does not belong to the world, which by this very process becomes an objective world." And this act of exclusion, this strategic stepping back, is what has allowed for the immense success of the objective, third-person perspective of science. But it is a success that has been achieved, as Schrödinger noted, at the high price of taking ourselves out of the picture. A complete and satisfying picture of the world, he argued, must somehow find a way to put the observer back in. The containment riddle is not just a puzzle for physicists and philosophers, it is a deep, existential reality that we all live with. We are both the subjects and the objects of our own experience. We are both the dreamer and the dream. And any final theory of reality that fails to embrace and account for this fundamental, paradoxical, and beautiful duality will be, at best, a partial and incomplete truth. The concept of a final theory, a single, complete, and consistent set of principles that would explain all the phenomena of the physical world, has been a powerful and enduring dream in the history of physics. The physicist Steven Weinberg, in his book, Dreams of a Final Theory, eloquently expressed this hope. Our present theories are of limited validity, still tentative and incomplete, but behind them now and then, we catch glimpses of a final theory, one that would be of unlimited validity and entirely satisfying in its completeness and consistency. String theory, with its potential to unify gravity and quantum mechanics, is often held up as the leading candidate for such a final theory. But is the quest for a final theory a realistic one, or is it a modern scientific version of an ancient religious quest for absolute truth against this modern dream of finality? We can contrast the medieval principle of learned ignorance, most famously articulated by the 15th century cardinal and philosopher Nicholas of Cusa. Cusa argued that the true path to wisdom lies not in the accumulation of knowledge, but in the growing awareness of our own ignorance. The more we know, the more we become aware of the vast, uncharted territory of what we do not know. This is not the simple, unlearned ignorance of the unaware, but a profound, learned ignorance, an enlightened state of humility and wonder. No man, Cusa wrote, can progress farther along the road to perfection than the point where he is found most knowing in the very ignorance that characterizes him. This is a perspective that resonates deeply with the current state of fundamental physics. Every major discovery, from relativity and quantum mechanics to dark matter and dark energy, has not led to a final, complete picture, but has opened up new, deeper, and more profound questions. The circle of our knowledge expands, but the circumference of our ignorance, the boundary with the unknown, grows with it. This suggests that the universe may be, in its very nature, inexhaustible. There may be no final theory, no bottom to the cosmic rabbit hole. Reality may be a series of nested, and perhaps infinite, layers of complexity and mystery. This is a humbling, but also deeply exciting, prospect. It means that the human adventure of scientific discovery will never be over. There will always be new horizons to explore, new puzzles to solve, new wonders to uncover. The quest for a final theory may be a necessary and powerful motivator for scientific progress, a guiding star that pulls us forward into the unknown. But perhaps the true wisdom lies not in the hope of one day arriving at a final destination, but in the journey itself, in the process of constantly expanding our knowledge and, in doing so, deepening our appreciation for the beautiful, infinite, and ultimately unknowable mystery of the cosmos. The choice between the dream of a final theory and the wisdom of learned ignorance is a choice between two different postures towards the universe, one of mastery and one of mystery. And perhaps a truly mature science, like a truly mature human being, will be one that can hold both. The very concept of space, which seems so simple and intuitive to us, has been the subject of a long and complex historical evolution, a journey that mirrors the development of our scientific and philosophical understanding of the world. From the heroic age of Greece until modern times, we can trace the development of two competing views, dressed space and undressed space. The idea of undressed space of a pure, empty void that exists in its own right, independent of the things it contains, was initially a radical and difficult abstraction. It was the view of the ancient Greek atomists, like Leucippus and Democritus, who proposed that reality consisted of nothing more than atoms moving in an infinite void. But for many, including the great philosopher Aristotle, this idea was nonsensical. A vacuum is nothing, he argued, and what is nothing does not exist. For Aristotle, space was always dressed, always filled with some kind of substance. He believed in a finite universe, with the Earth at its center, surrounded by a series of celestial spheres made of a fifth element, the ether. Beyond the outermost sphere of the fixed stars, there could be no space, because there was no matter, no ether, to fill it. This Aristotelian view of a dressed, finite space held sway for centuries. Medieval scholars, while grappling with the theological implications, eventually found a way to extend space beyond the sphere of the stars by inhabiting it with the omnipresence of God. But the idea of a true material vacuum remained a philosophical impossibility. In the 17th century, the French philosopher and scientist René Descartes also advocated for a form of dressed space. For him, the very definition of matter was extension, and so wherever there was space, there had to be matter. His universe was a plenum, a continuous, infinitely extended substance, with no possibility of a void. But the tide began to turn with the rise of experimental science. The invention of the air pump in the 17th century allowed scientists like Robert Boyle to create what appeared to be a vacuum in the laboratory, challenging the long-held Aristotelian and Cartesian views. This experimental evidence, combined with the immense theoretical success of Isaac Newton's physics, which was built on the concept of absolute, undressed space, led to the triumph of the Newtonian worldview. For the Newtonians, space was an infinite, eternal, and absolute container, a fixed stage upon which the drama of particles and forces played out. But the idea of a dressed space did not die. The discovery in the 19th century that light is an electromagnetic wave traveling at a finite speed raised a new question: what is the medium that is waving? Just as sound waves need a medium like air to travel, it was thought that light waves must need a medium to propagate through the vacuum of space. And so, physicists resurrected the idea of the ether, this time a luminiferous ether, a subtle, all-pervading substance that filled all of space and acted as the carrier for light. The advent of Einstein's special theory of relativity in 1905 finally did away with the need for an ether. Einstein showed that the speed of light is a universal constant, the same for all observers, and that the laws of electromagnetism do not require a special, privileged reference frame, which the ether would have provided. The undressed space of the atomists and Newton was reinstated, now unified with time, into the four-dimensional continuum of space-time. But the story does not end there. With Einstein's general theory of relativity in 1916, space-time was dressed once again, but in a new and far more profound way. Space-time was no longer a passive, static background, but a dynamic, physical entity. Its geometry curved and warped by the presence of matter and energy. And as we have seen, the development of quantum field theory in the 20th century has given space-time its final and most mysterious dressing, the zero-point energy of the quantum vacuum, the seething, energetic sea of virtual particles that fills every corner of the cosmos. The history of our concept of space is a beautiful, dialectical dance between the abstract and the concrete, between the void and the plenum, between emptiness and fullness. And what we have arrived at today is a vision that, in a sense, unifies these two ancient ideas. The universe is, at its core, a quantum vacuum, an undressed space in that it is the fundamental ground of being. But this vacuum is not an empty nothingness. It is dressed with a rich, dynamic, and endlessly creative energetic structure, a structure that is the very source of all the matter, all the forces, and all the complexity we see in the world around us. The nature of time, even more so than space, is a subject that has perplexed and fascinated the human mind since the dawn of thought. What, then, is time? Asked the philosopher St. Augustine in the 5th century. If no one asks me, I know what it is. If I wish to explain what it is to him who asks me, I do not know. These words still resonate with us today, capturing the deep, intuitive familiarity, and yet profound, conceptual elusiveness of time. We seem to experience time in a way that is fundamentally different from our experience of space. Space is the realm of the objective, the external, the world of things that we can see, touch, and measure with a meter stick. Time, on the other hand, seems to be the realm of the subjective, the internal, the world of our own, flowing stream of consciousness, of sensations, emotions, and ideas. And yet, modern physics has taken this subjective, flowing, and seemingly non-spatial experience of time and has, in a sense, spatialized it. It has stripped away many of the characteristics of the time we experience in our everyday lives, its flow, its transience, its division into a past, present, and future, and has made it akin to a dimension of space. Our physical world in the modern relativistic picture is a four-dimensional space-time continuum, a unified block of reality that contains all of space and all of time. This concept, which had its roots in the work of 19th century mathematicians and thinkers like Charles Hinton, was given its definitive form by Hermann Minkowski in the wake of Einstein's special theory of relativity. In a space-time diagram, the history of an object is represented by a world line, a line that traces its path through the four-dimensional continuum. A point on this diagram is an event, a specific location in space at a specific moment in time. The profound and unsettling consequence of this picture is that, in a very real sense, nothing ever happens in the space-time block. The entire history of the universe, past, present, and future, is laid out once and for all in a single, timeless, four-dimensional geometry. The restlessness of the world, its constant state of change and becoming, has been tamed, frozen into a static, eternal landscape. The philosopher William James dubbed this the block universe, a concept that does away with the very notion of a flowing now. In a tenseless, four-dimensional world, it is wrong to say that one event has happened, another is happening, and a third will happen. All events are simply there, at their specific coordinates in the space-time block. An object does not move along its world line from the past to the future. It simply exists at all the points along its world line simultaneously. The feeling of the flow of time, the sense of a moving now that separates a fixed past from an open future, is, in this view, a subjective illusion of our own consciousness. As the physicist Hermann Weyl wrote, "The objective world simply is. It does not happen, only to the gaze of my consciousness. crawling upward along the lifeline of my body. Does a section of this world come to life as a fleeting image in space which continually changes? This is a powerful and elegant picture, but it is one that comes at a high price. It leaves us with a deep and seemingly unbridgeable gap between the timeless, static, and objective world of physics and the transient, flowing, and subjective world of our own lived experience. The problem of transience, of how to account for our powerful and undeniable experience of a moving now, is one that physicists tend to dismiss as a psychological or metaphysical issue, not a physical one. But as the philosopher Gerald Whitrow pointedly asked, how do we get the illusion of time's transience without presupposing transient time as its origin? How can a world in which nothing ever changes give rise to an experience of constant change? This is the paradox that lies at the heart of our modern understanding of time. If the now is moving up our world line, at what speed is it moving? This question forces us to invoke a second dimension of time, and then a third, leading to the absurdity of an infinite, serial time. The spatialization of time, while a powerful and necessary tool for physics, seems to have left out the very essence of what time is for us, as conscious, living beings. The real problem, perhaps, is that we have tried to fit our rich, subjective experience of time into a purely objective, physical model. And in doing so, we have, as Schrödinger noted, taken ourselves out of the picture. A complete understanding of time may require a new kind of physics, a new kind of philosophy, one that can bridge the gap between the block universe and the flowing river, between the is of physics and the becomes of our own conscious experience. The puzzle of the arrow of time, the fact that the macroscopic world of our experience has a clear and unambiguous direction from past to future, is made even deeper by the fact that the fundamental laws of physics that govern the microscopic world are, for the most part, time reversible. The equations of motion for a single particle, the laws of electromagnetism, the Schrödinger equation of quantum mechanics, all of these work just as well for a movie played in reverse. And yet, the collective behavior of a large number of particles is clearly not time reversible. A mug of coffee on your desk will always cool down. It will never spontaneously heat up by drawing heat from the surrounding air. The flow of heat from hotter regions to cooler regions is a one-way street, a process governed by the second law of thermodynamics, the law of increasing entropy. This law provides the thermodynamic arrow of time. It seems that the arrow of time is an emergent phenomenon, something that arises from the collective, statistical behavior of many particles, but is not present in the laws that govern the individual particles themselves. It is like looking at a painting. If you look at a single dab of paint up close, you cannot tell which way is up. You have to stand back and look at the large-scale arrangement of many dabs of paint to see the picture and to know which way to hang it. In the same way, the arrow of time is not found in the microscopic details, but in the macroscopic patterns of the universe. We can visualize this in a space-time diagram. The world line of a single isolated particle has no inherent direction, but the world lines of the many particles that make up a hot cup of coffee are highly agitated. They are crinkled. And as time progresses, as we move up the diagram, this crinkledness, this agitation, spreads out to the neighboring, less agitated world lines of the surrounding air through collisions and other interactions. The system as a whole becomes more disordered, more crinkled on a larger scale. This process is not time reversible. If you were to turn the space-time diagram upside down, you would see agitation spontaneously concentrating from the cool air into the hot coffee, a clear violation of the second law. But this explanation just pushes the question back to the initial conditions of the universe. The second law only works because the universe started in a state of incredibly low entropy, a state of high order. The universe began with all its world lines in a very smooth, uncrinkled state, and the arrow of time is simply the story of the universe's long, slow, and inexorable journey towards a more crinkled, more disordered, and more probable state. Another, related, arrow of time is the electromagnetic or radiative arrow. The equations of electromagnetism are time reversible. They allow for both retarded solutions, where waves radiate outwards from a source into the future, and advanced solutions, where waves converge inwards onto a source from the past. In our universe, we only ever observe retarded waves. A light bulb emits light outwards. It never absorbs light inwards from all directions to become unlit. This is another fundamental asymmetry of our world, and it is also thought to be a consequence of the low entropy initial conditions of the universe. The cosmological arrow of time is the direction of the universe's expansion. The physicist Thomas Gold argued that this is the master arrow, that the future is, by definition, the direction in which the universe is expanding. This provides a clear directionality, but it raises the question of what would happen if the universe were to one day stop expanding and begin to contract. Would the arrow of time reverse? Would entropy start to decrease? Would people start to grow younger? This is a fascinating, if highly speculative, question. The current consensus is that the thermodynamic arrow of time would likely not reverse in a contracting universe. The processes that generate entropy are local and do not depend on the overall expansion or contraction of the cosmos. A contracting universe would likely continue its journey towards a state of higher entropy, culminating in a hot, dense, and highly disordered Big Crunch. All of these different arrows of time, the thermodynamic, the radiative, the cosmological, and the psychological arrow of our own memory, seem to point in the same direction in our universe. And they all seem to be rooted in the same deep and unexplained mystery, the incredibly special, low entropy state of the early universe. The arrow of time is not just a feature of physics, it is the very framework of our existence, the condition that makes life, memory, and causality possible. And the fact that this most fundamental feature of our reality is still not fully understood is a profound testament to the deep and enduring mysteries that lie at the heart of the cosmos. The basic parameters of our physical world, the fundamental constants of nature, seem, on the face of it, to be arbitrary and accidental. There is nothing in our current theories that explains why the speed of light has the value it does, or why the charge of the electron is what it is. They are numbers that we must measure experimentally and then plug into our equations. And yet, as we have seen, these numbers appear to be exquisitely fine-tuned to allow for the existence of a complex, life-bearing universe. This is the fine-tuning problem, and it presents us with a stark choice between two, very different, philosophical pictures of the cosmos. The first picture is the one offered by the anthropic principle in the context of a multiverse. In this view, our universe is just one of a vast, and possibly infinite, ensemble of other universes, each with its own, randomly assigned set of physical constants. The constants in our universe are accidental in that they are just one random draw from a vast lottery of possibilities. The reason we find ourselves in a universe with life-friendly constants is simply a matter of selection bias. We could not have found ourselves in any of the other, far more numerous, sterile universes. This is a powerful and scientifically respectable explanation, but it is one that many find to be philosophically unsatisfying, as it relies on the existence of an infinite number of unobservable realities and abandons the hope of a deeper, more fundamental explanation for the properties of our own. The second picture is the one offered by the bootstrap hypothesis. In this view, the universe is a single, unique, and completely self-consistent whole. There are no accidental or arbitrary features of a fundamental nature. The values of the constants, the properties of the particles, the very laws of physics themselves, are not random draws from a cosmic lottery, but are all fixed and uniquely determined by the requirement of overall mathematical and logical consistency. The universe is the way it is because it is the only way it could be. It pulls itself up by its own bootstraps. This is a much more aesthetically and philosophically appealing vision for many physicists. It is the dream of a final theory, a theory of everything that would have no free parameters, a theory from which all the properties of our universe could be derived from first principles. This was the dream that drove Einstein in his later years, and it is the dream that still motivates the search for a unified theory like string theory. In the bootstrap picture, the universe is not a random accident, but a mathematical necessity. In the absence of such a final bootstrap theory, The anthropic principle can be seen as a kind of makeshift or poor man's bootstrap. It is a way of establishing a relationship of self-consistency, not at the level of fundamental laws, but at the level of existence itself. It relates the properties of the universe to the existence of the organisms that observe it. When we observe a living organism, a wild flower, or a human being, we are also, implicitly, observing the universe that was capable of producing it, a universe with the right chemistry, the right stellar evolution, the right physical constants. The organism and its universe form a self-consistent, if partial, bootstrap loop. The ultimate hope of the bootstrap dream is that one day, our understanding will be so complete that we will be able to deduce the entire structure of the universe from the properties of a single, fundamental particle, like an electron. We will see, as the poet William Blake envisioned, a world in a grain of sand and a heaven in a wild flower. We will understand that the electron has the properties it does because it is part of a self-consistent whole, and that the universe has the properties it does because it is the only one that can contain a self-consistent electron. This is a vision of a universe that is not just a collection of contingent facts, but a deep, interconnected, and logically necessary unity. The choice between these two pictures, between the multiverse of chance and the bootstrap of necessity, is one of the central, unresolved tensions in modern fundamental physics. It is a choice that is not just about science, but about our deepest philosophical intuitions about the nature of reality. And it is a choice that may not be resolved until we have a final, complete theory of quantum gravity, a theory that can tell us whether our universe is a unique mathematical masterpiece, or just one beautiful, and very lucky, ticket in an infinite cosmic lottery. The quest to build a complete and satisfying picture of the universe, a cosmology that can account for all the phenomena of nature, is a journey that has led us to the very limits of our understanding, to the frontiers of space, of time, and of knowledge itself. We have traveled from the quantum foam of the primordial void to the eternal, self-reproducing landscape of the multiverse. We have explored the fiery crucible of the Big Bang, the strange, repulsive power of dark energy, and the deep, enduring mystery of the arrow of time. We have grappled with the paradoxes of quantum mechanics, the riddles of extra dimensions, and the profound philosophical implications of the anthropic principle. And in this grand intellectual adventure, we have been forced again and again to confront the limitations of our own human perspective. The containment riddle, the paradox of the observer who is part of the system being observed, is a stark and humbling reminder that any picture we create of the universe will be, by its very nature, incomplete. We are the mapmakers who are trying to draw a map of a territory that includes the mapmaker himself. This is a logical and epistemological puzzle that may never be fully resolved. It suggests that a final, objective, God's eye view of reality may be forever beyond our reach. The universe we know, the universe we study, is a participatory universe, a reality that is co-created in the dialogue between the cosmos and the consciousness that seeks to understand it. This does not mean that science is a purely subjective enterprise. The physical universe, as described by our scientific theories, is a powerful and remarkably successful model. It has allowed us to understand the workings of nature with incredible precision, to control our environment, and to create the technologies that have transformed our world. But it is a model, a map, a story. And it is a story that is, at present, profoundly incomplete. It has a gaping hole at its very center, the mystery of life and mind. Our physical theories can describe the dance of the atoms that make up a brain, but they cannot explain the subjective experience of consciousness that arises from that dance. They can describe the chemical processes of a living cell, but they cannot capture the emergent, holistic property of aliveness itself. The person who persistently asks, "Where is life in the physical world?" is passed from biologist to psychologist to physicist, each discipline admitting, in its own way, the limits of its own perspective. The buck, as the saying goes, stops with the cosmologist, because the cosmologist is the one who claims to study the whole thing. But the cosmologist, too, must confess a deep and profound ignorance. A truly adequate cosmology, as the philosopher Edwin Burt noted, will not be possible until we have an adequate philosophy of mind, one that can do justice to both the physical and the mental, the objective and the subjective, the outer and the inner aspects of our reality. The journey to understand the origin of the universe is, in the end, a journey to understand ourselves. We are not separate from the cosmos. We are a part of it. We are the universe's way of becoming aware of itself. The atoms in our bodies were forged in the fiery hearts of long-dead stars. The consciousness that is listening to these words is a product of a 14 billion year-long cosmic evolutionary process. And the questions we ask about the universe, its origin, its nature, its destiny are the universe's own questions, asked through us. This is a vision of our place in the cosmos that is both profoundly humbling and deeply empowering. It is humbling because it reminds us of our finitude, of the vastness of our ignorance, of the deep and enduring mysteries that will likely always lie beyond our grasp. But it is also empowering because it places us, as conscious, questioning beings, at the very heart of the cosmic story. We are not just insignificant specks of dust in a cold, meaningless void. We are the meaning makers, the storytellers, the observers through whom the universe comes to know and to wonder at its own magnificent existence. And as you lie on the threshold of sleep as your own, individual consciousness prepares to dissolve into the vast, mysterious, and creative ocean of the unconscious. You can feel a sense of participation in this grand, cosmic adventure. The journey is far from over. The greatest discoveries, the most profound insights, may still lie ahead. But the quest itself, the shared human endeavor to understand our cosmic home, is a journey that gives our fleeting lives a meaning and a dignity that can rival the stars themselves.
In the early dawn of knowledge, when philosophers still walked barefoot across the stone courtyards of Athens, the ideas of space and time were anything but obvious. To Aristotle, space was something filled with objects, with motion, with what the eye could see. Time, by contrast, was abstract. No one could see time itself, only feel it pass. It was a measure of change, but by what standard, and against what frame, remained elusive. Motion, for Aristotle, was not the consequence of force, as we later came to believe. It was an expression of change from potential to actuality. An object fell because it desired to return to its natural place. And that place was at the center of the universe. It was not law, but intuition, a way of understanding the world through philosophical reasoning rather than measurement. And thus, he reasoned, a heavier object would fall faster than a lighter one, for it bore more of its intrinsic nature. But every line of reasoning is born from the age that gives it breath, before clocks, before telescopes, before the very idea of speed. As we now understand it, how could one measure acceleration? How could one distinguish constant motion from changing motion? In that world, the idea that motion required a sustaining force made sense. A flying arrow, they believed, continued forward because the air behind it pushed it onward, a primitive notion of cause. From that, the logical conclusion followed: if nothing resisted motion, an object would move infinitely fast. This meant that a vacuum could not exist, for if there were empty space, then instant motion would follow, and if instantaneous motion existed, the world would unravel into absurdity. No force is infinite, therefore no motion should be. Space, then, must always be filled with something: air, water, fire, or a subtle invisible substance, what some would later call the ether. Still, in the faint cracks of ancient knowledge, another idea was beginning to bloom, one not from Aristotle, but from less celebrated thinkers like Democritus, Epicurus, and later, Lucretius. They imagined a world made of indivisible particles, atoms moving through infinite emptiness. It was a vision too bold for its time. How could nothingness exist? How could there be a place devoid of anything, yet still be real? Aristotle rejected such a notion, not only because it contradicted his philosophical intuition, but because it lacked an explanation for motion. Why did these atoms move at all? What set them in motion? The atomists replied, the universe has always been in motion. But that was not enough for Aristotle, who believed knowledge must seek causes, not merely describe appearances. The world kept turning, and time marched on. In the hush of the Middle Ages, small sparks began to glow in distant monasteries. Scholars like Philoponus, Hipparchus, and later, Roger Bacon and Robert Grosseteste began to question Aristotle. They experimented, measured, charted. They sought to unite the senses with numbers, intuition with proof. Through rough experimentation, they discovered that when two objects, one heavy, one light, were dropped, they fell at the same rate. This defied Aristotle's teachings but matched what they observed. Slowly, they realized that what changed an object's motion wasn't its essence, but something external, a force. A new concept emerged: momentum, what we now call inertia. An object, once in motion, would continue moving unless acted upon. This marked a fundamental shift from believing that motion required continuous force, to understanding that force caused change in motion, not motion itself. At that same time, a man named Leonardo da Vinci sat sketching observations of pendulums, flowing water, and falling objects. He lacked precision instruments but possessed something even more valuable: the eye of a careful observer. He began to notice that objects not only fall, they accelerate. From Leonardo to Galileo was a short step in time, but a long leap in thought. Galileo did not just observe, he measured, he experimented. Using inclined planes to slow falling objects, he measured intervals by the beat of his own pulse. And from this, he discovered that all objects in free fall accelerate at the same rate regardless of mass. A simple realization, but one that shattered thousands of years of Aristotelian thinking. Galileo also laid the foundation for measuring time, something no one before had truly done. He invented the pendulum clock, tuned the length of the cord to match regular intervals, and opened a door for physics, the door of law. But Galileo could not yet explain what kept planets circling the sun. He believed they moved in perfect circles because it was their nature, an echo of Aristotle still lingering. He overlooked or dismissed Kepler, who had already shown that planetary orbits were not circles, but ellipses. It was an omission, yet also a reminder no one reaches the truth alone. Science advances by relay, not by solitude. Meanwhile, in France, René Descartes was contemplating existence and space. He believed only one thing was certain: I think. Therefore I am. From that premise, he imagined a mechanical universe, a cosmos without emptiness like Aristotle. He believed that a vacuum was absurd. There could be no place where nothing existed. Every space must be filled. Every motion must result from contact. Every force must be a push or pull, not an action at a distance. He imagined the planets caught in invisible vortices, swirling cosmic whirlpools like pebbles carried in water. He could not accept that gravity might act without contact. That idea, he believed, defied reason. But that would later become the very thing he would confront in Newton. Christian Huygens, the Dutch physicist, continued the work of Galileo and Descartes. He calculated that objects in circular motion experienced inward acceleration, A equals V squared over R. He understood that circular motion was not natural, but required a force, the centripetal force, to keep an object from flying off. There was nothing remarkable about the apple itself. It fell, as all things fall. But to Newton, watching from the quiet of the orchard, the falling apple whispered of something deeper, a force that not only drew fruit to the ground, but might also hold the moon in its path. He began to wonder, what if the same invisible pull that brings objects downward also governs the dance of the planets? The thought was radical. Gravity, as Newton envisioned it, was not a push, not a vortex, not a mechanical shove from ether or air. It was a pull across emptiness, silent, instantaneous, reaching through the void. He did not explain how this force acted at a distance, only that it did. And in that silence, the world changed. With the publication of his Philosophiae Naturalis Principia Mathematica, Newton laid out laws that would govern motion for centuries. His first law, an object in motion stays in motion unless acted upon. His second, force equals mass times acceleration. And his third, for every action, an equal and opposite reaction. 3 lines that would become pillars of a new physics. 3 sentences that rewrote the language of nature. But it was his law of universal gravitation that unraveled the heavens. The same force that made the apple fall held the moon in orbit. The planets, too, obeyed this rule, drawn toward the sun, yet never falling into it, always curving, always missing, always returning. Gravity was not a local curiosity, but a universal principle. No longer was the cosmos a place of separate spheres. Earth and sky were one continuum, bound by the same invisible hand. It was a triumph of unity. For the first time, the motions of stars and stones could be explained by a single idea. The universe became knowable, predictable, and for a moment, almost tame. Yet Newton's world was not without mystery. In his formulation, gravity acted across empty space, but what carried this force? What medium connected two masses if nothing lay between them? He offered no mechanism, only mathematics. To some, that was enough. To others, it was a wound in reason. Action at a distance remained a phantom real in calculation, unfathomable in substance. Still, the predictive power of Newton's laws silenced most objections. Comets that once seemed like divine messengers now followed curves that could be charted. Tides, once the domain of myth, could be forecast by the moon's position. The universe, once veiled in mystery, now yielded its rhythms to calculation. But as Newton's vision took hold, something subtler began to shift. The universe was no longer a stage for gods and souls, but a machine, a vast clockwork mechanism wound at the beginning of time and ticking ever forward. In Newton's own words, God was necessary to set the system in motion, but once running, the laws required no further intervention. This idea spread quickly. Theologians resisted, poets lamented, but the age of reason embraced it. The world became geometry, the sky, a set of equations, motion, mere arithmetic of matter. The cosmos seemed infinite, eternal, precise, and disturbingly cold. Within this mechanical view, time became absolute. It ticked forward independently of events. Like the regular beat of a perfect clock, space, too, was fixed, a container in which objects moved. There was no curvature, no relativity, no distortion, just a blank stage upon which forces played. This model brought incredible success. Engineers, astronomers, and navigators thrived under its certainty. Yet in that certainty, some began to feel something had been lost. The cosmos, once alive with intention, became mute. There was no why, only how, no meaning, only motion. Philosophy receded as equations advanced. And yet, not everyone accepted this silence. In the salons of Europe, in the monasteries of Italy, in the halls of Königsberg and Geneva, thinkers began to ask whether the universe was truly so rigid. If time was absolute, how could it be felt so differently if space was fixed? Why did perception twist its shapes if nature was machine? Where was the human soul? These questions waited, for though Newton's universe explained much, it could not explain everything. Light, for instance, refused to obey the tidy rules of matter. It bent, it interfered, it defied understanding. And gravity, still mysterious, remained instantaneous, a troubling fact for those who believed in finite cause and effect. Across Europe, curiosity grew restless. The certainty of Newton had been a comfort, but comfort breeds questions. If the universe was indeed a clock, then who had wound it? And why did some of its gears seem to stutter strange gears, like magnetism, light, or heat, that refused to click into the mechanical pattern? The nature of light became a riddle that unsettled even the most confident minds. Was it made of particles, as Newton himself believed? Or was it a wave, like sound passing through air? Some experiments showed it bending around corners, interfering with itself like ripples on a pond. Others revealed that light could strike metal and knock loose tiny sparks. As if it were a bullet, not a wave, it behaved like both, and neither. It obeyed no single metaphor. And what of heat, that invisible fire which made metal expand and skin burn? Some called it a fluid, a substance named caloric that flowed from hot to cold. But this invisible substance could not be seen, trapped, or weighed. Others suggested that heat came from motion, the jostling of particles too small to see. If this was true, then everything solid and still was in fact dancing, trembling, alive beneath the surface. This view brought atoms back from philosophical exile. The ancient idea of tiny indivisible particles, once dismissed as metaphysical fancy, now gained foothold in chemistry and physics alike. Invisible though they were, atoms explained much: how substances combined, why gases expanded, why heat moved. The idea of a hidden world, a world of ceaseless, chaotic motion returned. Yet this invisible world raised strange dilemmas. If matter was made of atoms, what held them together? Why did some cling while others broke apart? And if everything moved endlessly, if time itself was stitched from motion, then what was motion through time? Could time change, slow, bend? Not yet, not in Newton's world, in his system. Time flowed uniformly, unaffected by the observer, but a few daring thinkers began to see cracks. One of them was a patent clerk in Bern, a man who thought deeply about what it meant to move, to measure, to observe. Albert Einstein, with quiet precision, dismantled the foundation beneath absolute time. He asked a simple question: what if the speed of light was always the same, no matter how fast you moved? The answer was not so simple. If light never changed speed, then time must, and space must. The very fabric of the universe had to stretch, warp, and shift, depending on how one moved through it. With that, Newton's absolute space and time were undone. The universe was no longer a fixed grid. It was a woven cloth, space and time stitched together, flexible, responsive, alive. Motion bent time, gravity bent space, mass became a measure of energy. Energy became fluid, shimmering, radiant. And gravity, that silent, unexplained pull, was no longer a force at all. It was a curve. Objects followed paths not because they were pulled, but because space itself was curved by mass. Planets orbited stars not like marbles tugged by strings, but like dancers following the bend in a floor they could not see. It was a new language for an old story. Newton's apple still fell, but now it fell not because it was pulled, but because Earth had curved the stage beneath it. And light, too, bowed its head to gravity, bending its path near stars, revealing that even something thought massless could be swayed by the shape of space. Einstein had not replaced Newton, he had deepened him. Just as Newton once made Aristotle a special case of a larger truth. So, Einstein made Newton's laws a shadow of a deeper structure, visible only at great speeds or near great masses. The clockwork cosmos had become a living geometry. Yet this geometry introduced its own enigmas. If space and time were relative, then what anchored reality if the universe could bend? Then could it twist into loops? Could time itself fold, allowing effects to precede causes? And if energy and matter were interchangeable, then what truly was substance? More unsettling still was what the new physics implied about the origin of the cosmos. If space could expand, then perhaps it had once been smaller, much smaller. Perhaps everything, time, matter, energy, had once been compressed into a single point, a beginning not just of things, but of being itself. The questions multiplied, the answers dissolved. Where Newton had drawn clean lines, Einstein sketched curves. Where Descartes saw machinery, Einstein saw elegance. The universe had not become less comprehensible, but it had become more mysterious. And mystery, once again, became the beginning of knowledge. The universe was no longer content to be seen. It now had to be imagined. In the dark silence between stars, space itself was growing, stretching not into something, but into itself. Galaxies receded not because they moved through space, but because the very fabric of space was expanding between them. It was not an explosion through a medium, but a swelling of the medium itself, silent, unceasing, without center. What had once seemed eternal now had a beginning, a birth not from chaos, but from a singularity, a point of infinite density, infinite temperature, infinite curvature, a place where the known laws of physics broke apart. The so-called Big Bang was not an outward blast from a location, but a beginning of space and time alike. There was no before, there was no outside. The cosmos began not within something, but as something. And yet, what emerged from that singularity was not chaos, but order astonishing. Fragile order, forces separated, symmetries broke, particles formed. The blueprint of all that would ever exist was imprinted in those first moments. A fraction of a second after it began, the universe knew how to build stars, how to shape galaxies, how to breathe atoms into being. But this precision was unnerving. Why should the laws be so finely tuned? Why did gravity have just the right strength to allow galaxies, but not too strong to crush everything into black holes? Why was the expansion rate so delicately balanced that it did not halt or tear itself apart? Why were the constants of nature so exact? as if written with intent. Some saw providence, others saw coincidence. Still others imagined multitudes a multiverse, infinite in variety, in which every possible configuration existed somewhere. In that vast landscape, our universe might not be special. It might simply be one of the few in which life could ask the question. But questions multiply in dark rooms. If space could expand, could it also tear? Could it form holes not just in space, but in the very order of cause and effect? General relativity permitted such structures, black holes, regions from which nothing, not even light, could escape. Not because something was pulling inward, but because the inward became all there was. The future, for anything crossing that boundary, pointed only deeper within, and what lay inside no one knew. The equations collapsed, space folded into space, time folded into time, mass became infinite, a singularity. Again, not at the beginning, but at the heart of unbeing. These were no longer philosophical riddles. They had become observable realities. Black holes were not just the fate of collapsed stars as they were real, detectable by their hunger, their shadows, their ripples in space-time. Einstein had not predicted them with joy, but with reluctance. He doubted they could form. The universe, he hoped, would not allow such monstrosities. But the universe allowed, and not just permitted, it required. Black holes formed not rarely, but often. They anchored galaxies. They shaped structure. They sculpted the cosmos like unseen hands. Where Newton had given us force, and Einstein had given us curvature, black holes gave us boundaries not physical, but conceptual. Inside their event horizons, all knowledge ended. No observer could report from within. No signal could return. In an age where physics had pried open the heavens, black holes were doors that remained shut. Yet even they were not eternal. As Stephen Hawking later showed, black holes could radiate slowly, imperceptibly. They could evaporate. Through a quantum whisper at their edge, information could bleed away. And with it came a final paradox. If black holes destroyed information, then the laws of physics which demanded reversibility would fail. A tear appeared between the smooth curves of general relativity and the jittering probabilities of quantum mechanics. They were both true, and yet together, incomplete. The universe at large obeyed one rhythm. The universe of the small danced to another. Between them lay a silence no theory could cross. In that silence, some imagined strings vibrating filaments, infinitesimal, whose modes of vibration gave rise to mass, charge, force. Others imagined loops, granular time, or emergent space, but none could yet bridge the gap. The quest for a theory of everything had become the quest for a language the universe was still unwilling to speak. In the search for unity, the questions had only deepened. The more the universe revealed, the more elusive its heart became. What began as a desire to understand motion had led to a trembling awareness of mystery, not for lack of knowledge, but because knowledge had reached its edge. It was not just the cosmos that grew strange, but consciousness itself. If space could curve and time could stretch, then what of the observer in quantum theory? The act of observation changed the outcome. Particles existed in clouds of possibility until measured, as though reality itself required a witness. The boundary between world and mind blurred. Was consciousness merely an emergent function of matter, or was it somehow woven into the very fabric of being? Some thought of the ancient Pythagoreans, who had believed that number and harmony governed all things. Others recalled the mystics, who spoke of the illusion of separateness, the unity behind form. Modern physics, in its own way, had circled back to such riddles, not in doctrine, but in implication. The vacuum, once dismissed by Aristotle as absurd, now seethed with energy, a sea of fluctuations. Particles appearing and vanishing in ghostly pairs. Emptiness was no longer empty. Even nothing, it seemed, was something. And the universe itself, it still expands, accelerating with an energy no one can name. Dark energy. They call it not because it is understood, but because it is not. It pushes galaxies apart with a silent force, shaping the fate of everything, yet remaining beyond reach. Dark matter, too, passes unnoticed through all we see. It outweighs the visible stars, yet never shines. It holds galaxies together like scaffolding made of shadows. It neither emits nor absorbs light, but its gravity carves the shape of the cosmos. The familiar now floats in a sea of the unknown, all that we call atoms, stars, and light is but a sliver, a small island of the comprehensible amid a vast ocean of the hidden. And time, that old companion, may not be eternal. Some theories speak of a heat death, a future in which stars burn out, black holes fade, and all gradients dissolve. A universe of uniformity, cold and still, where nothing more can happen. Others imagine cycles, rebirths, bouncing cosmologies where the end curls into a beginning. But even if the cosmos fades, the questions remain. Why do laws exist at all? Why should anything be ordered, measurable, or beautiful? Why is there something rather than nothing? No equation has answered that. No telescope has glimpsed its edge. We ask not because we are ignorant, but because we are aware. We seek not merely to explain, but to belong. The universe, in its vastness, does not speak, but it allows us to listen. From Aristotle's unmoved mover to Newton's universal law, from Einstein's curvature to the quantum veil, each step has drawn us deeper, not into certainty, but into awe. Perhaps the ultimate lesson is not how the universe works, but that we can ask it all. That in a corner of space, for a brief span of time, there are minds capable of wonder. And wonder, like gravity, pulls us forward.